One day, the Mediterranean Sea will no longer exist. The Strait of Gibraltar, that narrow strip of water you can see across on a clear afternoon, will be gone, and Spain, Portugal, and Morocco will probably become a single, unbroken landmass. This is not science fiction, this is geology. And despite it will only happen in a few million years, the process is already happening right now, beneath your feet as you watch this video. Let's talk about it. Imagine you're holding a giant puzzle. The Earth's surface is like that puzzle, broken into big pieces called tectonic plates. These pieces float on hot, gooey rock deep underground, and they very slowly move around. Now, Spain and Portugal, together called the Iberian Peninsula, are sitting on one of these puzzle pieces, and scientists have just discovered something remarkable. That piece is slowly rotating, like a clock's hand, but incredibly slowly. And here's the thing about a rotating puzzle piece. It no longer fits where it used to. If you tried to push it back in, you'd have to shave off the edges around it. It would be wobbly and imperfect, but eventually it would settle into a new position. The puzzle is never going to look the same again, and if you wanted to hold it all together for good, you'd reach for the strongest glue you have. And once it sets, what were two separate pieces become one single, larger, immovable chunk. That is exactly what awaits Spain, Portugal, and Morocco. Over millions of years, the slow rotation and the relentless pressure of colliding plates will push them together until they fuse into one continuous landmass. A new giant piece of the puzzle that will never come apart again. But let's back up a little, because to understand why this is happening, you need to understand what's actually going on underneath our feet. The Earth's crust is not one solid shell. It's cracked like the shell of a hard-boiled egg that you've dropped on the floor. Those cracks divide the surface into large sections, those tectonic plates we mentioned, and they're constantly on the move. Not fast enough to see or feel or even measure without very precise instruments, but they move. And two of the biggest ones, the African plate and the Eurasian plate, have been on a slow-motion collision course for millions of years. Right now, they're creeping toward each other at a pace of about 4 to 6 millimeters per year. That's roughly the length of an ant. Sounds like nothing, right? But add that up over 1,000 years and you've got about 20 feet, the length of a decent-sized yacht. Add it up over 1,000,000 years and you're talking about up to 3.5 miles of movement. The Earth doesn't rush. It doesn't need to. Now, if you open Google Maps and zoom in on the very bottom tip of Spain, you'll spot a tiny little strip of land jutting out toward Africa. That's Gibraltar, the narrow channel of water separating Europe from Africa. And when we say narrow, we mean it. At its tightest point, the strait is only about 9 miles. On a clear day, you can stand on the Spanish coast and see Morocco with your own eyes. Two continents close enough to almost touch, and getting closer every single year. Nobody alive today will ever see them merge, not our children, not our children's children, not anyone's for millions of generations to come. But we're here to think big, so let's keep going. The place where the African and Eurasian plates meet, just south of the Iberian Peninsula, has frustrated geologists for decades. Unlike most plate boundaries, which are sharp, clean, well-mapped lines, this one is blurry and complicated. The two plates don't just collide cleanly here. They grind, they overlap, they push sideways, and the result is a messy zone of stress and deformation that scientists are still trying to fully understand. To get a better picture, a team of researchers combined two types of data: readings from GPS satellites orbiting the Earth and records of earthquakes that have occurred across the region over recent decades. By looking at how the crust is being squeezed and warped at that boundary, they were able to map the underground stresses. And what they found confirmed something that had long been suspected but never clearly proven. The Iberian Peninsula is performing a slow, clockwise rotation. Here's why, and this is where it gets really interesting. Just east of the Strait of Gibraltar, there's a geological structure called the Gibraltar Arc. Think of it as an enormous underwater mountain range that curves in a wide arc, like a bent arm, connecting the mountains of southern Spain on one side and the mountains of northern Morocco on the other. The Baetic Cordillera runs through southern Spain, sweeping from the coast near Cadiz all the way to the Sierra Nevada. On the African side, the Rif Mountains in northern Morocco form the other end of this arc, and between them, mostly submerged beneath the sea, lies the arc itself. Now, this structure is not sitting still. The entire Gibraltar Arc is slowly drifting westward, toward the Atlantic, and as it moves, it stretches and curves, almost like a slow-motion wave rolling toward the ocean. And here's the crucial part. As it does that, it acts like a natural shock absorber. All that enormous pressure generated by the African and Eurasian plates grinding into each other, east of the strait, the Gibraltar Arc soaks most of it up. It takes the hit so that the rest of the Iberian Peninsula doesn't have to. The stress gets absorbed into the arc's own deformation rather than transmitted further inland. But west of the strait, the arc's protection runs out. There's no buffer, no shock absorber, nothing standing between the two colliding plates and the southwestern corner of Iberia. The African plate pushes directly into it, like pressing hard on one corner of a revolving door, and that uneven pressure is precisely what causes the whole peninsula to rotate clockwise. The east is somewhat shielded, the west is getting pushed, and the result is a slow, grinding twist that's been building for millions of years. Now, you might be thinking, okay, fascinating, but what does any of this have to do with my life? Fair question, but here's the thing. You might be closer to this than you think. The most direct way these tectonic forces make themselves known is through earthquakes. The southwestern part of the Iberian Peninsula, around Cadiz, Sevilla, and southern Portugal, is one of the more seismically active regions in all of Western Europe, precisely because of this pressure, and historically has already shown us what happens when that pressure gets released all at once. In 1755, Lisbon was hit by one of the most catastrophic earthquakes ever recorded. It leveled the city, killed tens of thousands of people, and sent a tsunami rolling across the Atlantic Ocean. That earthquake was a direct product of the exact same tectonic forces this research is describing. Beyond earthquakes, the movement shows up in subtler ways too. GPS satellites are now sensitive enough to detect that specific points on the Iberian Peninsula are shifting by a few millimeters every year relative to the rest of Europe. And the mountain ranges of southern Spain, the Sierra Nevada and the Beatic Cordillera, are still being actively pushed upward by this compression. They're technically still growing, just far too slowly for anyone to notice. The same goes for the Rif Mountains across the water in Morocco. The rotation is happening all around us. It's just that most of its consequences play out on a timescale that makes an entire human life feel like a single frame in an extraordinarily long movie. And the ending of that movie? The Mediterranean Sea gradually closes. Africa and Europe join at the western end. The Strait of Gibraltar disappears, replaced by mountains and rock and a continuous landmass stretching from Scandinavia all the way to the Sahara. It sounds almost impossible, but the forces making it happen are already at work. Right now, beneath your feet, one ant's length at a time. A leftover chunk of an ancient tectonic plate is on the move beneath North America, right under the southern part of the Cascadia subduction zone. This isn't some harmless debris. It's a real slab of Earth that never fully disappeared. And because it's still sliding around down there, it could be adding a whole new layer of stress to a region that already has a reputation for massive earthquakes. The story started with weird signals showing up in seismic data. It's basically Earth's X-ray. Scientists send waves through the ground and watch how they bounce back. These waves started acting wrong beneath the Pacific Ocean off the western US coast. Instead of smooth, predictable patterns, researchers saw a giant, coherent block deep below the seabed, moving differently from everything around it. It didn't look like a landslide, didn't look like loose debris, and didn't behave like normal ocean crust. That's when someone dared to ask the question out loud. What if this is something much older and much bigger than we thought? Some researchers seriously wondered if this could be a remnant of a lost continent, maybe a forgotten shard of Pangaea, the supercontinent that once stitched almost all land together. Technically, it's not fully impossible. Continents break, sink, stretch, and vanish over millions of years. This fragment was enormous, solid, and oddly shaped, which made it hard to classify. It didn't fit into the usual categories scientists use to explain underwater structures. Then came the slow, careful reality check. Scientists brought in more data, better models, and deeper analysis. They measured the age of the rock, studied how seismic waves bent through it, and compared its motion to known plate movements. That's when the picture shifted. This wasn't a lost continent at all. It was something just as dramatic, but far more dangerous. A massive leftover fragment of an ancient tectonic plate. This fragment turned out to be a survivor from the Farallon Plate. This ancient plate once dominated the Pacific, but got mostly swallowed as it slid beneath North America millions of years ago. Most of it vanished into Earth's mantle, but not all of it went quietly. This chunk survived like a splinter that never fully sank. Researchers named it the Pioneer Fragment, and the name fits because it's charting territory we didn't even know existed. And this fragment isn't just drifting harmlessly, it's moving horizontally beneath North America, which is weird and dangerous in geological terms. Normally, plates collide or slide past each other in predictable ways. This fragment behaves like a wrench jammed into a machine that already runs under insane pressure. The West Coast already balances on fault lines that store stress like stretched rubber bands. Add a giant moving rock slab underneath, and suddenly the system becomes harder to predict, harder to model, and much harder to feel safe about. The region where this fragment lurks already scares geologists. You've got the San Andreas Fault, famous for snapping without warning. You've got the Cascadia Subduction Zone, capable of producing earthquakes so powerful they rewrite coastlines. Now, scientists realize there's a hidden player deep beneath the ocean floor, something satellites can't see, and scientists can't directly observe. This fragment doesn't follow clean, predictable rules. Think of it like stacking dominoes on a table that's already shaking. It moves slowly, but in geology, slow movements still means unstoppable force. And when that built-up energy is finally released, it won't care about evacuation plans or building codes. There's also a timing problem that nobody likes to talk about. Geological processes don't run on human clocks. Stress can build for centuries and snap in seconds. The Pioneer fragment might trigger something tomorrow, or it might sit quietly until generations forget about it. That uncertainty makes planning brutally hard. Cities like Los Angeles, San Francisco, and Seattle already prepare for known earthquake threats. Now, scientists must consider a system that can amplify disasters in ways nobody has practiced for. So, scientists now race to update models, improve seismic imaging, and understand how this fragment interacts with nearby faults. They know they can't stop earthquakes. All they can do is reduce surprises. And it's also clear that sometimes the most dangerous threats aren't coming from space, but sliding quietly beneath the sea. Another recent ancient landmass discovery wasn't nearly as dramatic, but super important for science. It started as a sand dredging operation off the coast of Indonesia, but then archaeologists found more than 6,000 fossil fragments from a lost submerged ice age landmass. Among them were 140,000-year-old Homo erectus remains. That single find forced scientists to rethink how early humans lived, moved, and interacted across Southeast Asia. For a long time, researchers assumed the Homo erectus population on Java lived cut off from everyone else. But those dredged-up fossils proved that Java wasn't an island. It sat right in the middle of a massive Ice Age landmass called Sundaland. Indonesia, Malaysia, Borneo, Thailand, and Vietnam are all connected into one enormous landscape. But we now call islands like Java, Sumatra, Borneo, and Bali were linked together through huge river systems that probably rivaled the Amazon. Dense forests stretched across the land, giant animals roamed freely, and wide coastal plains existed where ocean waves sit today. And Homo erectus didn't just survive there, they thrived. And no, this wasn't a snowy wasteland, unlike how we mostly imagine the Ice Age. Sea levels dropped more than 400 feet because so much water was locked up in glaciers. When that happened, massive chunks of the ocean floor rose above the surface like natural stepping stones. Early humans didn't need boats.
They could literally walk from mainland Southeast Asia to places we now think of as isolated islands. They moved while tracking animals, exploring open land, and following food sources. It worked like a giant prehistoric highway system. When the Ice Age ended, glaciers melted like forgotten ice cream cones on a hot sidewalk. Sea levels rose, slowly at first, then fast. Rivers overflowed, coastlines vanished. Entire human landscapes slipped beneath the waves. Over thousands of years, Sundaland drowned, and the people who lived there had to adapt or move to higher ground. Now, archaeologists piece together this lost world bone by bone, artifact by artifact. Every new discovery pulled from the seabed brings us closer to rewriting the story of early human migration. Studying submerged landmasses and lost continents is a work that takes years. In 2017, scientists made an announcement that changed this universal truth that there are 7 continents in the world. The discovery of Zealandia. Zealandia's story ties straight back to Gondwana, the ancient supercontinent that started breaking apart hundreds of millions of years ago. Around 80 million years ago, Zealandia split off too. But while Australia stayed high and Antarctica mostly held its ground, Zealandia slowly sank. Only a small chunk stayed above sea level, even though many geologists argue it still qualifies as a full continent. That little bit you can actually see today is mostly New Zealand, along with a few nearby islands that also belong to Zealandia. By the end of 2025, scientists had finished mapping the northern 2/3 of it, covering nearly 2 million square miles of submerged land. Researchers dredged rock samples all the way from the Fairway Ridge to the Coral Sea. They pulled up all kinds of material: pebbly and cobbly sandstone, fine-grained sandstone, mudstone, bioclastic limestone, and even basaltic lava. And these rocks came from wildly different time periods. When researchers lined all this up, they saw something big. The internal stretching from both Zealandia and West Antarctica caused the crust to thin and crack in a way similar to subduction. That cracking let ocean water rush in and helped form the Tasman Sea. A few million years later, Antarctica continued pulling away, stretching Zealandia's crust even more until it thinned so much that sinking became inevitable. This directly challenges the older idea that Zealandia broke apart mainly through sideways strike-slip motion. The team also thinks the direction of that stretching shifted by as much as 65 degrees, which likely helped the continental crust thin out way more than expected.
Monaco seems powerful. Wealthy people and Instagram influencers walking outside the casino, posh cars pulling up to elite residences, and a tiny cup of coffee that costs more than a kilogram of freshly roasted beans you could enjoy at Café de Paris. Over 700 under Grimaldis, the same family. This place seems invincible, but this luxury veneer is more fragile than you think. This seemingly unsinkable power could be destroyed within minutes by something far more powerful than money: nature. Well, it's not actually only about Monaco. The French Riviera is pretty long, and the danger hangs over not just France, but Italy too, especially the Liguria region in the northwest. I know you may be watching this video from somewhere far away, and these places may not ring a bell to you, but you've definitely seen them before, at least as a screensaver once in your life. Well, this beauty could one day be buried under an extremely powerful tsunami. And if the word tsunami gives you Japanese vibes, we can make it à la française and call it radomare or maremoto in Italian. It's true that when most people hear the word tsunami, they imagine giant waves crashing into the coast of Japan, Indonesia, and other countries bordering the Pacific. For decades, the Mediterranean Sea seemed different, smaller, calmer, and far removed from the world's most famous tsunami disasters. But scientists and international organizations are now warning that this perception is misleading. A tsunami in the Mediterranean is not a distant possibility. According to experts, it's something that will almost certainly happen again within the next few decades. Yes, again. The French Riviera has already experienced more than 20 documented tsunamis, the most recent one taking place in October 1979. And strangely enough, it was not caused by nature alone. It was more like an unlucky chain of events. At the time, Nice Airport was undergoing a massive expansion project. Authorities wanted to extend the runway farther into the sea and build a new harbor area. Was it really necessary? Honestly, probably yes. If you look at the map, you'll realize Nice is basically the only major airport serving this whole part of the Riviera. Cannes does have an airport, sure, but it mainly serves private jets. Monaco only accepts helicopters, so technically it doesn't even have an airport. The two closest large commercial airports are in Marseille, about 200 kilometers away, and Genoa in Italy, around 190 kilometers away. Turin is technically another option, but driving there means crossing difficult alpine roads, and the train takes more than 4 hours. So yes, Nice desperately needed that expansion. But during the construction works, a massive underwater landslide was suddenly triggered beneath the sea. Huge amounts of mud and rock collapsed downward like an avalanche underwater. This movement displaced enormous amounts of water and created tsunami waves that struck around 60 miles of coastline. In Antibes, the waves reached more than 11 feet high. The disaster took up to 23 human lives and caused flooding, as well as major property damage. And that's the scary part about tsunamis in this region. They do not always need giant Hollywood-style earthquakes. Sometimes a collapse beneath the sea is enough. The Mediterranean is smaller and more enclosed than the Pacific Ocean, which means waves can travel toward the coast very quickly. In some places, people may only have minutes to react. So, could something like this happen again? Did the locals learn their lesson? Well, construction along the Riviera never really stops. Nice is currently going through major urban transformation projects as part of a push toward modernization and sustainability. While the historic center and the Promenade des Anglais remain mostly untouched, there are still significant construction zones around the port, Nice West, and the airport area. Nobody is saying current construction will directly trigger a tsunami, but UNESCO is still issuing serious warnings. Their monitoring programs and scientific assessments indicate that there is effectively a 100% chance that the Mediterranean will experience at least 3 tsunamis over 1 meter high within roughly the next 30 years. And 3 feet may not sound very large at first, but tsunami waves behave very differently from normal beach waves. They carry enormous amounts of fast-moving water and energy. Even relatively small tsunamis can flood streets, damage buildings, overturn vehicles, and place thousands of people in danger. This very part of the Mediterranean is unique. It has everything packed together: sea, mountains, and dense coastal cities. In some places, like Menton, the geography is truly one of a kind. Menton is shielded from cold northern winds by the Alps and the Prealps. This traps warm Mediterranean air, giving the town more than 300 days of sunshine every year, and some of the warmest winters on the Côte d'Azur. The city itself is tiny. You could literally walk across it in under 2 hours, and the buildings are pushed very close to the coastline. At the same time, the population density is pretty high, and huge numbers of tourists arrive every year for the Lemon Festival and all things lemon-related. Now, imagine a place this tiny hit by a tsunami. Horrible, right? The tsunami danger specifically in Menton comes from 3 main things: nearby earthquake faults, steep underwater terrain, and crowded beaches during summer. And the key issue is that the danger is not far away. It's literally sitting right offshore. Beneath the sea near Menton lies a giant crack in the earth called the North Ligurian Fault System. It sits only about 12 to 18 miles offshore. Deep underground, 2 giant pieces of the earth, the African plate and the European plate, are constantly pushing against each other. Most of the time, the movement is slow and invisible, but sometimes pressure builds up until the ground suddenly jerks upward. When this happens beneath the sea, the water above gets pushed upward too, almost like someone slamming a hand into a bathtub. That sudden movement can create a tsunami within minutes. This already happened in 1887 during a large earthquake in the Ligurian Sea. The earthquake affected cities across Italy and France, including Genoa, Savona, Nice, Menton, and even Caen. People reported something terrifying. First, the sea suddenly pulled backward, exposing parts of the beach that are normally underwater. Then the water rushed back toward the coast as a wave. Earthquakes near Menton also triggered underwater landslides. Huge amounts of sand and mud can suddenly collapse downhill beneath the sea, like giant avalanches underwater. When all that material moves at once, it pushes water aside and can generate dangerous waves. Even earthquakes happening far away in North Africa can sometimes send tsunami waves across the Mediterranean toward the French coast. What makes this even more dangerous is how calm the sea usually looks. Menton's sea has very small tides, so the water often appears peaceful and harmless. Because of this, many visitors never imagined that a tsunami could happen there. And during summer, the beaches become packed with families and tourists. If a large wave arrived suddenly, evacuation would become extremely difficult. Now, let's rewind for a second to the Ligurian Sea, because the name may have sounded a little strange earlier. Yes, it does exist. Technically, it's part of the Mediterranean Sea, but many people refer to it separately because of its geography. It sits between northwestern Italy, the French Riviera, and islands like Corsica and Elba. And this entire area is particularly vulnerable. The African and European tectonic plates are colliding right beneath this region. That collision created the beautiful mountains everyone admires today. But it also causes earthquakes, which means many famous cities in this region sit directly inside an active geological zone. Genoa, Pisa, Florence, Nice, Antibes, Menton, and of course, glamorous Monaco, right on the coast. The same force that created the Riviera's beauty is also what makes it dangerous. And because so many towns here are squeezed tightly between mountains and the sea, there's very little room to escape if a tsunami suddenly arrives. That is exactly why scientists and emergency agencies are becoming increasingly worried about this coastline.
A network of deep faults runs right beneath Seattle, and it can shift at any moment, affecting millions of people. The consequences could be as catastrophic as in the past, when a devastating quake lifted the seafloor, collapsed shorelines, and triggered a massive tsunami. It happened in the winter of the year 923. A powerful earthquake hit what is now the Seattle area. It reached around magnitude 7.5, and the impact was terrifying. The ground didn't just shake violently, it shifted. Shorelines collapsed, parts of the seafloor lifted upward, and a tsunami swept through Puget Sound, flooding coastal areas. This event came from the Seattle Fault Zone. This is a complex system of faults that runs directly beneath modern-day Seattle, and it's still active today. This makes it one of the most dangerous geologic threats in the Pacific Northwest. Now, what threat does it present? Well, if a similar earthquake happened now, it would hit a densely populated region, putting millions of people at risk. It would also cause billions of dollars in damage to buildings, roads, and infrastructure. Scientists have started studying this fault more closely to understand how often it produces major earthquakes. They looked at the past 11,000 years to analyze time gaps between large seismic events. Well, the results are kinda mixed. On the one hand, devastating earthquakes, like the one that hit in 923, seem to be extremely rare. In fact, it's the only known quake of that size, magnitude 7.5 or higher, linked to this fault zone. So we can hope that the worst-case scenario, where massive earthquakes like this happen often, is unlikely. But researchers have also made a rather worrying discovery. Smaller earthquakes happen more frequently than expected. And while these quakes may not reach magnitude 7.5, they can still damage buildings, crack roads, disrupt utilities, and trigger landslides. In a modern city like Seattle, even a moderate earthquake can cause really serious problems. In other words, the region still faces regular seismic risk. The fault is active, the pressure builds over time, and the ground can move again. The real danger is the ongoing threat of smaller but still destructive earthquakes, and they may strike with little warning. Now let's take a closer look at the Seattle Fault Zone. It's this huge fault system sitting right under Seattle, a whole network that stretches about 46 miles from the mountains east of the city, all the way to the water on the west side. And yes, it runs directly under Seattle. It's a thrust fault, which means one chunk of ground is slowly pushing up over another. That pressure builds up for a long time, and then suddenly releases. That's when you get a big earthquake. Scientists didn't really start digging into this until the 1990s, when they noticed strange gravity readings. Plus, they found signs that a tsunami had hit the area about 1,000 years ago. All of that pointed to one thing: something catastrophic happened here before, most likely that huge earthquake back in 923. But there was a problem. The data they had managed to gather only went back about 5,000 years. This certainly isn't enough to see a clear pattern. So researchers decided to dig deeper and turn to something called marine terraces. These are old coastlines that got pushed upward by earthquakes and now form something like steps along the shore. Now, an important detail. The 923 earthquake lifted the land by about 26 feet. So scientists started looking for other terraces with the same kind of shift. They mapped out more than 150 of these terraces around Puget Sound, measuring their height and adjusting for natural slopes. It turned out that only one event in an 11,000-year window caused a big uplift like that: the 923 earthquake. As for smaller quakes, those could be hidden under layers of sediment. It means that huge city-shaking earthquakes are very rare, possibly with 5,000 years or even more between them. But it doesn't mean the danger is gone. Smaller ones are what we should worry about. They hit way more often, and they can do serious damage. That's why researchers focused on smaller side faults. Those are called blind faults because you can't see them at the surface, but they can still trigger strong earthquakes, and they already have. One of these smaller faults caused a magnitude 6.7 quake in the past. That's strong enough to damage buildings, crack roads, and mess up infrastructure. So the team pulled together a bunch of tools, like magnetic scans, fieldwork, LiDAR maps. They even dug trenches across fault lines and used dating methods to figure out when past quakes occurred. In the end, they found 3 more earthquakes. One happened around 11,000 years ago. One more hit in the early 1800s. That's a pretty big gap. But it proves these smaller faults have been active for a long time. But the most worrying thing is that these quakes didn't line up with movement on the main fault. That means the smaller faults can rupture on their own. When the team added all this new data together, they saw a pattern. Smaller quakes hit about every 350 years over the last 2,500 years. That's more frequent than scientists used to think. And this activity seems to have picked up over the last 2,000 years. Now, researchers are trying to figure out how big these quakes can actually get, how often they hit, and what would happen if one struck today. But it's not so simple. They have to piece the whole picture together from rocks, layers of soil, and tiny clues they find underground. So, where does it leave Seattle? Well, there's a national system called the Seismic Hazard Model. It's what engineers and planners use to decide how strong buildings need to be, how to design infrastructure, that kind of thing. Right now, this system includes the big 923-style quake, but it doesn't really account for the smaller side faults. First of all, these faults are shorter than what the model usually considers. Second, we're still unsure about how powerful their quakes can get. That's why the model should probably be updated, and authorities need to start planning for those more frequent quakes. It could directly affect building codes and safety plans. Now, despite this worrying news, there are other even more dangerous faults on Earth. Like the San Andreas Fault, it cuts through California for about 800 miles. It's where two massive plates slide past each other sideways. That constant grinding builds pressure and then releases it fast. That's how you get quakes like the 1906 San Francisco disaster. Today, millions of people live right on top of it, so scientists track every, even the tiniest tremor with sensors, watching for signs of a bigger break. Then, there's the North Anatolian Fault that runs about 930 miles across Turkey. It tends to break in a chain reaction, one quake triggering the next along the line. In 1999, one of those breaks hit Izmit and took the lives of over 17,000 people. Now the stress is building closer to Istanbul, and that's a city with over 15 million people. The Sumatra subduction zone in Indonesia is where one plate dives under another, locking up tons of energy. In 2004, it unleashed a magnitude 9.1 quake and a tsunami that more than 230,000 people didn't survive. It's still active today, and scientists constantly monitor the seafloor and ocean pressure to catch tsunami signals as early as possible. The Alpi Belt stretches over 1,500 miles from southern Europe to Asia. It once helped build mountain ranges like the Alps. Here, plates crash into each other and push land upward. Quakes don't occur here often, but when they do, they can be powerful and hit heavily populated regions. Japan also sits right where several plates collide. It's one of the most earthquake-prone places on Earth. In 2011, a massive offshore quake triggered a tsunami and the Fukushima disaster. Since then, Japan has built one of the most advanced monitoring systems in the world. Thousands of sensors track ground movement in real time to send out warnings within seconds. It turns out that the Great Pyramid of Giza is even more advanced than we thought. It can handle earthquakes with magnitudes of at least 6.8, and that's a big one. During powerful quakes, while nearby buildings were collapsing to the ground in ruins, the pyramid just absorbed the shaking and stayed standing. Was there a secret mechanism that helped it? More than 4,500 years ago, ancient Egyptians built one of the heaviest structures in human history, the Great Pyramid of Giza. Pharaoh Khufu ordered its construction around 2500 BCE, and it took about 26 years to finish. Workers dragged and stacked more than 2.3 million stone blocks, and some of them weighed several tons each. The finished pyramid was about 480 feet tall. It's just a bit lower than the Ritz Tower in Manhattan, which reaches 541 feet. But that might not even be the most shocking part. The pyramid was likely built to handle earthquakes. Recently, researchers from Egypt and Japan decided to study how vibrations move through the pyramid. Now, the pyramid is over 4,600 years old, so they didn't want to shake it on purpose and risk damaging it. But they still managed to test about 40 different spots inside and around the giant structure with the help of special equipment called highly sensitive accelerometers. Their tools measured tiny waves moving through stone. Ultimately, it could help them figure out what would happen if the ground started shaking. It turns out that instead of concentrating all the force of vibrations in one place, the pyramid spreads the energy through the structure. In simple words, it behaves like a giant shock absorber. The vibrations weaken while moving through the pyramid, instead of building up and cracking it apart. Egypt has been shaken by earthquakes many times over thousands of years. Some of them were strong enough to wreck entire parts of Cairo. And while some nearby buildings were badly damaged or completely destroyed, the Great Pyramid is still standing. Scientists say that the structure is incredibly balanced. The huge weight is distributed so evenly that the pyramid remains stable even when the ground moves underneath it. The shape helps too. A pyramid pushes weight downward and outward, and this makes it harder for its parts to collapse inward. For example, in 1992, a massive earthquake hit Egypt. It had a magnitude of 5.9, and its epicenter was about 20 miles southwest of Cairo. It damaged or destroyed more than 129,000 buildings. Old tombs near the Valley of the Kings had to be reinforced so they wouldn't collapse. But the Great Pyramid didn't really care, having lost just one stone. One big reason is the pyramid's design. Its base is enormous, more than 755 feet wide. That wide bottom helps spread out force and keeps the structure stable during shaking. The pyramid is also extremely symmetrical. This helps balance pressure from all sides. Plus, underneath, there's solid bedrock that acts like a super strong foundation. Then, there are the blocks themselves. Ancient builders used huge limestone blocks that lock together like giant puzzle pieces. During an earthquake, such a structure can absorb and spread vibrations. It won't crack apart right away. The Great Pyramid wasn't Egypt's first attempt at pyramid building. Earlier rulers had already been experimenting for many generations. For example, more than 100 years before Khufu, Egyptians built the step pyramid at Saqqara. Instead of having smooth sides, it looked like giant stone stairs. Later, Khufu's father started building larger pyramids with smooth outer sides, much closer to the famous pyramids we know today. Over time, Egyptian builders kept learning what worked and what failed. Yep, some later pyramids tried cheap shortcuts. One pyramid used part of a natural hill to save materials. But that made the structure less stable because fewer blocks locked together. Another pyramid, called the Black Pyramid, was built mostly from mud bricks. True, it was cheaper, but also much weaker. No wonder it aged horribly. Rain and erosion slowly destroyed the structure. Some of those later pyramids eventually collapsed completely. But let's get back to the Great Pyramid and its earthquake survival skills. Scientists actually went inside it and measured its vibrations. They studied places like the King's Chamber, the Queen's Chamber, underground tunnels, and hidden rooms above the King's burial chamber. They found out that the entire pyramid vibrated almost perfectly evenly from one stone block to another. It means that the whole construction moves together as one giant object instead of shaking apart in different directions. And that's the most important thing during an earthquake. Now, the ground around the pyramid vibrates very differently, at a much lower frequency. So, when the earth shakes, the pyramid doesn't fully sync up with those dangerous vibrations. And that helps reduce the force moving through the structure. Imagine pushing someone on a swing. If your timing matches the swing, it goes higher and higher. But if the timing is off, the movement weakens. The pyramid seems to work the same way with earthquakes. Scientists also discovered something else inside the structure. Above the King's Chamber, there are several small relieving chambers. And no, they aren't bathrooms. Before, many people thought that they only help support the weight of the ceiling. But now, researchers believe that those chambers may also help weaken earthquake vibrations before they reach the most important inner rooms. In other words, the pyramid must be redirecting and softening shock waves inside itself. Overall, the pyramids are much more amazing than we think. They aren't simply giant tombs built by slaves. Archaeologists found entire workers' villages near the pyramids. The builders had houses, food, medical care, and organized work teams. They were skilled laborers and got paid for their work. They needed those skills and a lot of strength. After all, some of the limestone and granite blocks weighed 80 tons. That's heavier than a fully loaded semi-truck. And they came from quarries miles away. So, how did the workers move them? Well, One theory claims that they use wooden sleds moving on wet sand, or probably there were special lubricated paths. So far, we haven't figured this mystery out yet. The pyramids also look completely different back then. Today, they look kinda rough and dusty, but originally, they were covered in smooth white limestone. It was polished so brightly that the sunlight reflected off the pyramids like mirrors. Inside the Great Pyramid, the temperature stays close to 68 degrees Fahrenheit almost all the time, even when the desert outside gets scorching hot during the day and freezing at night. The massive stone walls work like giant insulation. The Great Pyramid also lines up almost perfectly with north, south, east, and west. That means the ancient Egyptians understood astronomy better than most people think. The pyramid might have even been an observatory, not just a tomb. Now, there's another mystery of the Great Pyramid: hidden chambers. Using thermal cameras and muon radiography, researchers have detected empty spaces inside the pyramid. But we can't reach them yet, so no one knows what's in there. Of course, there are theories: secret rooms, lost knowledge, hidden chambers, or something that could change how we see the pyramid completely. Because the strange part is, even though the pyramids are supposed to be tombs, no one has ever found a mummy inside the Great Pyramid. The whole complex is huge. Giza isn't just 3 pyramids. There are smaller satellite pyramids, temples, worker villages, and long walkways connecting everything. The whole area shows how much planning went into these structures and how important they were to the ancient Egyptians. And the math involved is cool too. The Great Pyramid's base covers about 13 acres, and if you take the perimeter of the pyramid and divide it by the height, you'll get roughly 3.1416, that's pi. The ancient Egyptians managed to do it without modern tools, and scientists still don't understand how. Then, there's the alignment with the stars. Some researchers have proposed that the 3 main pyramids at Giza line up with the 3 stars in Orion's belt. If it's true, that might not be an accident. The ancient Egyptians believed that their pharaoh's souls would rise to the sky through that constellation. The next global disaster won't begin with a meteorite or a giant tsunami. The culprit might be warm ocean water. A powerful climate pattern called El Niño could develop in 2026, and it may become the strongest one in more than 100 years. In the past, a similar El Niño triggered droughts and a famine that wiped out up to 60 million people. Now, El Niño is a climate pattern that starts in the Pacific Ocean. Huge areas of water near the equator become much warmer than normal. And we're not talking about a tiny patch of ocean. That warm water can spread for thousands of miles. When that happens, weather all over the planet goes crazy. Some places get massive floods, while others stop getting rain completely. Winds shift, storms move, and seasons change. And that's exactly what might have triggered the disaster in 1876. Massive droughts spread across Asia, Africa, and South America. Rain disappeared for months, and rivers dried up. Crops failed over enormous areas. Over the next 2 years, millions of people were slowly starving. Historians think that up to 3% of the world's population didn't survive this disaster. Even today, it remains one of the most fatal catastrophes in human history. Scientists believe that the El Niño from the late 1870s may have been one of the strongest ever recorded. Now, how did they figure it out? Obviously, nobody had satellites in the 1800s. There were no weather apps or climate models or modern instruments. So researchers had to investigate the past almost like detectives. And one of the biggest clues came from trees. You see, every year a tree grows a new ring inside its trunk. In wet years, the rings grow thicker because the tree gets more water and grows better. During droughts, the rings become thin and weak. So trees basically store weather records inside themselves. Scientists studied giant drought atlases built from tree rings gathered from all over the world, with some of those records going back hundreds of years. And they showed something alarming. Apparently, during the famine years, huge parts of the planet experienced extreme drought at the same time. Then, researchers checked old rainfall records from thousands of weather stations worldwide. Finally, they compared them with ocean temperature records gathered by sailors in the 1800s. All the evidence pointed to the same thing. The Pacific Ocean likely seriously warmed up during those years, and that's exactly what happens during an El Niño. But that one may have been way more extreme than normal. The event likely lasted around 16 to 18 months, several months longer than many other El Niño events in recorded history. That extra time matters a lot, because the longer the Pacific Ocean stays unusually warm, the longer weather systems around the world remain broken. Some regions experienced droughts for several seasons in a row. Rainfall dropped to record lows in several parts of the planet. It hit Asia especially hard. Scientists found that parts of Asia went through the worst drought in about 800 years. Crops failed across huge regions, instead of only one country or one farming zone. The thing is, a drought alone does not automatically lead to mass starvation. But when huge crop failures happen at the same time as food shortages and bad transportation, millions of people can suddenly end up with no food reaching them. And that's exactly what happened during the global famine. Anyway, El Niño could explain why weather patterns broke down across multiple continents at once. Even though modern technology makes us far more advanced than people from the 1870s, we still depend on stable weather for food, farming, water, and electricity. And El Niño has the power to disrupt our planet on a gigantic scale. The most unsettling part is that the past disaster was not caused by some single freak event. Researchers believe that those conditions develop naturally, and Earth's climate system is very capable of producing something this extreme again. Today, the world is much hotter than it was in the 1870s, so if another Super El Niño appeared in the future, could droughts become even more severe? An El Niño can mess with the weather almost everywhere on Earth at the same time. One of the first big changes often happens during hurricane season. Normally, the Atlantic Ocean produces many tropical storms and hurricanes. But a strong El Niño can create powerful winds high in the atmosphere. Those winds basically tear storms apart before they can fully grow. So, places like the Caribbean and parts of the Atlantic sometimes see fewer hurricanes during strong El Niño years. But in the Pacific, it's the opposite story. Storm activity often ramps up in the central and eastern parts of the ocean. That can bring trouble for places like Hawaii, and sometimes even the southwest U.S. if storms move in that direction. Then winter hits, and this is when El Niño starts shaking things up in North America. The northern U.S., western Canada, and Alaska usually turn warmer than normal, and some areas get less snow. But it doesn't mean these regions don't have winter. Cold snaps can still show up out of nowhere. At the same time, the southern U.S. often gets wetter. A stronger jet stream, which is basically fast wind high in the sky at around 30 to 45,000 feet, pushes more storms across the south. They bring heavy rain, flooding, and cold weather to regions that are usually much drier. Other parts of the world can get hit even harder. For example, India and parts of Southeast Asia often lose important summer monsoon rains during El Niño years. And those rains are critical because hundreds of millions of people depend on them for farming and water supplies. The monsoon weakens, drought spreads fast. The Caribbean also gets much drier than normal during a strong El Niño. In some areas, there are even water shortages and crop damage. In Southeast Africa, drought conditions can become dangerous during the Southern Hemisphere summer, especially from December to February. A powerful El Niño may already be building in the Pacific Ocean right now, and some researchers think it could become one of the strongest ever recorded. Ocean temperatures in part of the Pacific are heating up fast. In some places, the water might become more than 5 degrees Fahrenheit hotter than normal. But for the planet's climate system, this difference is massive. The danger is actually even bigger than it looks. Today, we have better technology, satellites, forecasting, global communication. But our society still has weak spots. Food supply chains are actually under pressure, and many regions are also dealing with drought. Ocean temperatures have been breaking records for years. Some farming areas are becoming less stable because of the weather changes. Extreme weather events are becoming more spread out every year. A strong El Niño could pour gasoline on all of that. Scientists are especially worried about how unpredictable the weather could become over the next year. Oh, by the way, El Niño is just part of a big cycle. Normally, winds near the surface of the Pacific Ocean, called trade winds, blow from east to west. They push warm, sun-heated water toward Asia. At the same time, colder water rises up from deep below near North and South America. This is the reason why the ocean surface ends up uneven. The water near Indonesia can be about 1.5 feet higher than near Ecuador. But sometimes, those winds weaken. When that happens, the warm water starts sliding back toward the east. The eastern Pacific heats up, and the western side cools down. That's an El Niño. If the opposite happens and the trade winds get stronger, even more cold water rises from the deep ocean. As a result, the Pacific cools down more than usual. That phase is called a La Niña. El Niño and La Niña are basically two sides of the same system. Together, they're part of a cycle called ENSO. Usually, an El Niño lasts about 9 to 12 months, while La Niña can stick around for 1 to 3 years. But not all El Niños are the same. The classic type is called an Eastern Pacific El Niño. That's the one where the eastern side of the Pacific warms up the most. But there's another kind called a Central Pacific El Niño. In this case, the warmer water sits more in the middle of the ocean.
For the first time ever, we saw the shape of a supernova explosion in real time. The blast was so immensely powerful that it was literally ripping the surface of the star right in front of our eyes. Now we can finally understand what actually happens inside a star right before it blows apart. You see, massive stars fight against their own gravity their whole lives. They burn hotter and hotter elements to keep themselves from collapsing inward. But eventually, the star starts producing iron in its core. And this is a problem. Unlike many other elements, iron doesn't create energy inside the star. So once this process starts, the star loses its support system and gravity wins. The core collapses inward insanely fast, and then everything around it crashes down toward the center of the star. Once all that falling material slams into the dense core, it rebounds and creates a gigantic shockwave, and that's what rips the star apart. Scientists didn't fully understand how that part worked, but new observations helped them. They could watch the shockwave while it was actually moving through the outer layers of the star. Even better, they could see the shape of the explosion, and it wasn't what anyone expected. The blast wasn't perfectly round. It was slightly stretched in one direction. It may sound unimportant, but it can actually change how we understand supernovas and their final moments, when a star suddenly releases more energy than our sun will produce during its entire lifetime. The exploding star was first spotted on April 10, 2024, by a system called ATLAS, which scans the sky for dangerous or unusual objects. Just a few hours later, scientists already pointed one of the world's most powerful telescopes, the Very Large Telescope in Chile, directly at the discovery. For a very short time, the star's real shape and the shape of the explosion were both visible. But soon after, clouds of superheated gas hid everything. The star was a red supergiant. That's an enormous star close to the end of its life, about 12 to 15 times heavier than our Sun. Normally, when we think of a supernova, we imagine a giant flash of light illuminating space. That flash happens when the shockwave from the collapse gets through the star's outer layers and releases a truly enormous amount of energy. For many months, the explosion shines brighter than whole galaxies, but the first few hours are the most important, and usually impossible to study because they pass super quickly. This time, scientists used a special technique that studies how light waves move and scatter. It helped them notice that the exploding material looked almost olive-shaped. Later, the explosion slammed into the gas surrounding the star and its shape flattened. But it still kept the same overall direction even while it was expanding outward into space. That detail may actually help us solve one of the biggest mysteries about supernovas. Right now, scientists have two main ideas about what can actually cause a giant dying star to explode. The first idea claims that tiny particles called neutrinos blast out from the collapsing star and heat everything around them, but the heating happens unevenly. So, the explosion becomes messy and unstable. That's why the star blows apart in a rough, uneven way. There's another theory. It sounds much more extreme. Some scientists think that the star sends out enormous streams of energy from deep inside its core right before exploding. These streams work like giant cosmic drills. They punch through the star and force the explosion outward in a more organized direction. The new supernova can tell us which idea is closer to the truth. The telescope data showed that the explosion had a very clear shape and direction almost from the very beginning. It didn't look random or chaotic. The blast stayed surprisingly symmetrical while it expanded through space. And that's a big clue. The explosion looked more like something fueled by powerful streams of energy rather than a messy neutrino blast. This discovery changes a lot. For decades, researchers have been arguing over what really happens inside a massive star during its final seconds. And now we can finally figure out the mechanism behind those gigantic explosions. And if you think that all supernovas happen insanely far away from Earth and don't affect us in the least, let me tell you this. Right now, Earth is drifting through the leftovers of a giant explosion that happened somewhere in space a very long time ago. And scientists just found some proof inside ancient Antarctic ice. Researchers were studying ice that had formed up to 80,000 years ago and discovered tiny traces of something called iron-60. You see, most iron on Earth is a normal version called iron-56, but iron-60 is different. It's radioactive, extremely rare, and it slowly disappears over millions of years. And it usually forms during supernovas. In simple terms, scientists found microscopic pieces of star ash frozen inside the ice. At first, researchers were confused. The Antarctic snow where they discovered this kind of iron was less than 20 years old. It made no sense. If a nearby star had exploded recently enough to spray this material onto Earth, we would have definitely noticed this. The sky would have lit up with one of the biggest cosmic explosions in history. But there was no supernova. This meant something else was going on. Eventually, they figured out the truth. Apparently, our entire solar system is currently moving through a gigantic cloud of gas and dust. Scientists call it the local interstellar cloud. For years, researchers suspected that this cloud may have formed after one or more huge stars exploded nearby a long time ago. And now, the discovery of iron-60 proves this idea. The material likely came from an ancient supernova that once sent its radioactive debris across space. Even after all this time, tiny particles from that explosion are still floating through our region of the galaxy, and some of them are literally falling onto Earth. To test the idea, scientists dug into old deep-sea sediments and ancient Antarctic ice cores going back 30,000, 40,000, and even 80,000 years. And every deeper layer gave them more evidence. The levels of iron-60 changed over time exactly the way they would have if Earth had been slowly drifting through a giant cloud filled with ancient supernova debris. and its microscopic radioactive particles have been falling on our planet for thousands of years. By the way, iron-60 was extremely difficult to find. Scientists started with around 660 pounds of Antarctic ice. After processing it, they started searching through trillions of atoms to spot just a few tiny traces of iron-60. But the search paid off. Researchers are sure that this ancient stellar debris may help us better understand the strange clouds surrounding our solar system. We can also learn more about the powerful cosmic events that had been affecting our galaxy before we even existed. Now, it might come as a surprise, but many of the elements you're made of come from supernovae. It can be anything, from the oxygen you breathe to the calcium in your bones. The iron in your blood or the silicon in your computer might have first appeared in the core of a star. And when a supernova exploded, it unleashed a storm of nuclear reactions, which in turn produced lots of building blocks making up the world around us. Supernovae are like giant particle machines in space. When a star explodes, the blast wave crashes into the gas around it and creates a super powerful magnetic storm. Tiny particles get trapped inside, bounce around, and speed up to insane speeds. Eventually, some of those particles shoot across space as cosmic rays. And then, some of them hit Earth. They slam into our atmosphere, smash into our atoms, and create invisible showers of particles that rain down on us all the time. The Panama Canal is beginning to collapse. This is one of the most important shortcuts in the world, and nearly 6% of everything shipped by sea goes through it. But when water levels dropped, fewer ships were able to get through, and companies had to look for other ways to move goods. Now, a new billion-dollar rail corridor is taking shape in Mexico, and it could change the future of shipping forever. We'll get into that bold project in a moment, but first, we need to understand why the Panama Canal matters so much and why we need other options fast. So, the Panama Canal is basically a 51-mile man-made passage between the Atlantic and the Pacific. It was constructed back in 1914, and today it's considered one of the two most strategic waterways in the world. The other one is on that level in the Suez Canal. To see why it matters so much, let's look at a map. If a ship sails from the east coast to the west coast of the United States, it would normally have to go all the way down to Cape Horn at the southern tip of South America. But with the Panama Canal, that trip is about 8,000 nautical miles shorter. So yeah, it's a huge difference. It's not just the US that benefits from it. The Panama Canal also saves a lot of time for ships traveling between Europe and East Asia or between Europe and Australia. It also helps ships move more quickly between ports from one side of North America to the other side of South America. The Panama Canal is like the perfect solution. It gave the world a faster and easier way to move goods between countries. Around 14,000 ships go through it every year. Those ships carry more than 500 million tons of food, minerals, and manufactured products. That's about $270 billion worth of cargo. This passage was built and controlled by the US at first, but since 1979, PANA has been in charge. Keeping this canal running has become a huge challenge recently. The country has been hit by severe drought over the last 3 years, and when it doesn't rain enough, water levels in the canal drop, so ships get stuck. A big part of the problem was caused by the well-known El Niño. This natural phenomenon makes ocean waters in the central and eastern Pacific warmer, and that completely changes weather patterns in many parts of the world. In the US, for example, that often means warmer weather in the north and wetter conditions in the south. In Panama, it usually means drought and less rain. Thanks to it, the region got about 40% less rain than usual from late 2022 to 2024. That is a huge problem for trade, because the Panama Canal relies completely on rainwater to operate. Lake Gatun, one of the canal's main water sources, started drying up too. The lake normally sits around 87 feet, but it fell to just 81.8 feet. As the water level dropped, they had to cut the number of ships allowed through the Panama Canal. Normally, about 34 ships cross it every day, but at one point, that number fell to just 18. The result was a traffic jam, with some ships stuck waiting for about 3 weeks to get across. That quickly turned into a much bigger problem for global trade. The traffic slowed down the flow of key products around the world. We're talking about things like oil, grain, canned food, iron, steel, and a lot more. And when ships started piling up like that, prices usually started climbing too. So companies had to find other ways to move their products. That's far from ideal, because the other routes are much longer, slower, and more expensive. Let's say a product is coming from China to the US East Coast. Instead of going through the Panama Canal, the ships might have to go through the Suez Canal, adding about 7 days to the trip. And if it is headed to the US Gulf Coast, it may have to go all the way around the Cape of Good Hope, which can add at least 10 more days. All that extra time means extra costs, and the rates on major trade routes went up by 20 to 30%. A lot of e-commerce shipments got caught up in this too. Deliveries started slowing down, especially in Latin America. Some companies then started shipping their products by plane, and that's a lot more expensive. That extra cost usually gets passed on somehow, either through higher shipping fees or higher prices. When that happens, some people may just stop buying from certain online stores. That's bad for everyone. Things are a little better now though. The region was recently affected by La Niña, which is the opposite of El Niño. This brought heavy rain back to the area and Gatun Lake filled up again. It actually came close to its maximum level in early 2026. That was a huge turnaround after the extremely low levels of the past few years. Okay, traffic on the canal is still lower than it was before the drought, but at least things are moving again. Getting the water levels back up was a huge relief, but it may not last. Specialists now believe El Niño could return later in 2026. In fact, they're even talking about a possible super El Niño, the kind that can push global temperatures to record highs. If that happens, the region could be hit by another round of severe drought, and it could be even worse this time. So if things slow down in the Panama Canal again, what's the other option? Well, Mexico may have an answer. For years, they've been working on a rail route in the south of the country to connect the Pacific Ocean to the Caribbean Sea. It's called the Tehuantepec Interoceanic Corridor, or CIIT for short. The idea is not new at all. It goes all the way back to 1907, but only now is it finally starting to become real. This massive infrastructure project was approved in 2019, and since then, it has received around $4 billion in investment. Its main goal is to compete with the Panama Canal, but it's also meant to do much more than that. They want it to bring new industry into the towns and cities along the route and help turn southern Mexico into a major center for logistics and manufacturing. The plan is built around 3 new rail lines, but that's only part of it. They will also upgrade 2 major ports along with new industrial projects, gas pipelines, and highways. And to attract private companies, Mexico is also offering major incentives across 4 states: Veracruz, Oaxaca, Chiapas, and Tabasco. Basically, the idea is to move some shipments across Mexico by train, instead of sending them through the Panama Canal. That could ease some of the pressure and give companies another way to move their goods when problems start piling up. The project is expected to be fully completed by June 2026, but it's already up and running. Not long ago, Hyundai tested the route by moving 900 vehicles on the CIIT rail line. Before, a shipment like this would take about 6 days to cross Mexico, but with this new rail system, it took just 9 hours. That's why authorities say the CIIT could become a key route for moving goods from the Pacific to the Atlantic, and vice versa. That is where things stand today. The Panama Canal is still a key route for global trade, but it's under more pressure than ever. At the same time, Mexico is building a bold new alternative that could open a different path between 2 oceans. It's still too early to say how far this project will go, but one thing is certain. When one of the world's most important trade routes begins to slow down, everyone starts searching for what comes next.
South Korea has uncovered a massive deposit of a special clay called illite. the largest known reserve of its kind on Earth. It could help clean dirty water and polluted soil, making farming better, and used in new things like cosmetics and construction materials. In simple terms, it could mean cleaner places to live and better everyday products like cosmetics, chemicals, paints, plastics, and many others. But first things first, what's so special about this illite? It's not rare like gold or lithium, and it's not flashy. It's closer to ordinary dirt, but a very special version of it. Think of it as a superfine natural clay with some pretty unusual properties. It can act like a natural filter, something like a sponge that can trap harmful substances. For example, it can help absorb heavy metals, reduce bad chemicals, and even fight bacteria. It might also help remove odors and give off far infrared heat. That's a type of gentle heat you can't see but can feel. Because of that, people sometimes call it a mysterious mineral. This clay mineral forms slowly over time in places like lake beds or river sediments. You can find it buried under layers of rock. It's not sparkling or metallic, it just looks like soil. But on a microscopic level, it behaves very differently. If regular sand is like a pile of marbles, smooth and not very interactive, illite is more like a stack of sticky, layered sheets with lots of surface area, and those tiny layers can grab onto other particles and ions. So imagine polluted water flowing through soil. Heavy metals in water spread easily and stick to things, causing problems wherever they go. Illite acts like a filter wall. It doesn't just block them, it also pulls them in and holds them on its surface. That property explains why so many industries care. In environmental cleanup, it can behave like a natural detox layer, trapping unwanted metals before they spread further. In construction, it can go into building materials to make things stronger or more stable. In farming, they add it to soil and fertilizers to help plants grow better and use it in animal feed like a natural additive to keep them healthy. In cosmetics, tiny clay particles can grab and hold on to dirt and oil. It's a bit like face masks that pull impurities out of your skin. And in industrial materials, illite can be mixed into products to change how they react with moisture, chemicals, or heat. Here's just one of the numerous examples. Studies showed that bean sprouts grown with illite ended up getting more nutrients. They had about 1.9% more vitamin C and 11.2% more minerals compared to normal sprouts. It probably sounds small to you, but in agriculture, even a few percent improvement is a big deal. Anyway, this enormous deposit of illite was discovered in Yongdong County in North Chongqing Province, and the total amount of material there is likely about 104.5 million tons. That's basically a mountain of materials hidden under the ground. For example, most large clay deposits in the world are around 5 million tons, so this one is about 20 times bigger. Even famous deposits in countries like China only reach a few million tons, and this one completely dwarfs them. Because of all of this, Yongdong County now wants to turn extracting illite into a whole industry. The idea is not just to dig it up and sell it, but to build a whole system around it. I mean, creating official standards and quality checks. Scientists explored the area by drilling 28 deep holes into the ground. It was like sticking giant straws into the earth to see what's inside. To their surprise, they found very high-quality material. About 2/3 of it was in a sweet spot range. It's the area where the mineral is especially pure and useful. In some parts, the rock was found to contain up to 98% illite. Imagine finding almost pure chocolate in a chocolate cake. Uh-oh, now I'm hungry. We can look at illite as a tool. The idea is that it could help clean things up, especially water and soil. When dirty water flows through polluted soil, it can carry harmful chemicals. Illite grabs onto those metals and traps them, like a magnet picking up iron filings. Once it's trapped, the bad stuff can't really spread. That's why researchers are so interested. This clay might fix lots of problems, like cleaning contaminated land or improving water quality in places where industry has left some damage behind. Picture pollution like paint spilled into water and soil. In this case, illite is like a giant cleaning cloth that soaks up part of that mess before it spreads further. But let's dig into the details. In 2026, Yeongdong County released results from a long research project they did together with the Korean Institute of Geoscience and Mineral Resources. It took about 2 years, from 2024 to 2026, and involved a lot of serious groundwork, drilling deep holes into the earth, scanning underwater like a medical CT scan, and then building a 3D model of what's below the surface. The results, as you know, were better than anyone could have hoped for. South Korea invested about 23 billion won, which is around $15.5 million, into a special research and industry center. The goal was to test, standardize, and develop new products from illite in a controlled way. They're also trying to connect with international scientific groups, like the Clay Mineral Society in the US, to create global standards for what counts as high-quality illite. Now, this whole green miracle mineral idea really depends on technology. In the lab, illite can look amazing. It can clean water, trap metals, and improve soil. But the real work is way messier. One batch of illite might work perfectly, and another might fail, just because the grains are slightly different or because there are tiny impurities mixed in. That's why standard rules and certification mean so much. Without them, it's like selling medicine with no dosage control, which is risky and unpredictable. Then there's the scale problem. Right now, production is still very small. Reports say local output was around 2,000 tons in 2024 and dropped to about 665 tons in 2025. Now compare that to the estimated 104.5 million tons underground. The deposit is huge, and turning it into something useful at a large scale is a serious challenge. And we should keep in mind that mining still means digging up land, moving rock, creating dust, running heavy machines, and burning energy in the process. Trucks have to move the material, and factories have to refine it. All this leaves a really bad impact on the environment. Is illite worth it all? Well, to judge that, we need clear data, real reports on environmental impact, and clear plans for restoring the land after mining. And we need transparent tracking of where the material actually goes. Illite comes from shallow ground. It means we don't need to dig deep mines and can reach it relatively close to the Earth's surface. But workers still use heavy machines to dig it out. They break the clay into large chunks first, then crush it into a very fine powder so different industries can use it. After crushing, they clean the material. Natural clay always mixes with other materials like sand, quartz, and feldspar, so they remove those unwanted parts to improve quality. Next, the powder is refined. Its color and texture can be adjusted, and it can be made finer for use in cosmetics, construction, or industry. For more advanced processing, engineers heat the material to get rid of bacteria or remove unwanted organisms. They also use mild chemical treatments to change how the clay works. For example, to pull out needed elements used in fertilizers. In some cases, they modify the surface of the particles so the clay mixes better with other materials in products like fillers or skincare products. Now, to get the purest illite, scientists mix it with clean water and separate it by particle size. The smallest particles, usually under 2 micrometers, sink or separate out differently. And exactly those tiny particles contain the richest and most useful clay material.
The United States didn't neatly grow into 50 states. The map we see today is more like the result of a lot of attempts, negotiations, and a surprising number of ideas that almost worked but didn't quite make it. At different moments in history, entire regions, like parts of North Carolina and Tennessee, tried to split off and become states of their own, and some of them, like Delmarva Peninsula, came very close.
part of the reason is how the system itself is built. States can shape their own rules on things like taxes, schools, business regulations, and even parts of criminal law. So everyday life in California can feel very different from life in Ohio. But they're still tied together under one national framework. There's one constitution, one overarching set of rules that all states have to follow. What really drives these breakaway ideas is something simpler: people feeling overlooked. In a country this large, some regions start to feel like decisions are being made far away by people who don't really understand their situation. Over time, that frustration turns into a question: what if we just handled things ourselves? So here are 12 places that tried. Start with Scott in northeast Tennessee. In 1861, when Tennessee chose to side with the Confederacy, Scott County pushed back. Locals didn't agree with that direction, so they declared themselves the free and independent state of Scott and stayed aligned with the Union. No one formally recognized it, but what's interesting is how long the idea stuck. Scott County never officially reversed that decision until 1986. For over a century, it quietly carried this identity, almost like a historical footnote that never got erased. Now go north to Michigan and the idea of Superior. Michigan looks simple on a map until you notice it's split into two separate landmasses. The Upper Peninsula sits far from the main population centers and developed a different identity, more focused on mining and forestry, less connected to the urban South. That gap led to repeated calls for a split, basically a divorce between the two halves. The idea goes back to 1858 and has resurfaced many times. In 1959, someone even filed a lawsuit to try to make the separation official. It didn't succeed, but the fact that it reached that level says a lot. Even today, you'll still hear occasional talk about it. Out west, there's Lincoln. This one keeps reappearing in different forms. The general idea is to combine eastern Washington and northern Idaho into a new state. It first showed up around 1865 when people in northern Idaho felt cut off after the capital moved further south. Since then, the idea has come back again and again. In 1901, the 1920s, and even as recently as 2005. Each time, the reasoning is similar. Rural inland communities feeling disconnected from coastal or urban centers like Seattle. A bit further south, you get Jefferson, which is almost a mirror version of Lincoln. It would combine Northern California and Southern Oregon. The idea dates back to the 1850s during the gold rush, when remote communities wanted more local control. The most dramatic moment came in 1941. Supporters staged a kind of theatrical protest, blocking highways and handing out declarations of independence. It caught attention, but then global events shifted focus overnight and the movement faded. Decades later, in 2013, several counties in California voted to explore the idea again. Nothing changed officially, but the identity of Jefferson still exists and even has its own flag. Then there's Absaroka in the late 1930s, covering parts of Wyoming, Montana, and South Dakota. This one grew out of the Great Depression. Rural communities felt like they weren't getting enough support compared to larger towns. A local official, A.R. Swickard, stepped forward as a leader and started acting like the head of a new state. They created license plates, held public meetings, and even crowned a Miss Absaroka. It sounds unusual, but it worked as a signal. Attention increased, resources followed, and once conditions improved, the movement faded away. Now compare that to Sequoia, which was far more structured. In 1905, several Native American nations in what is now eastern Oklahoma proposed forming their own state. Their goal was to maintain control over their land and systems. They organized a full constitutional convention, drew up laws, mapped out counties, and held a vote that strongly supported the plan. It was one of the most complete statehood proposals ever made, but Congress turned it down, mainly to avoid shifting the political balance. Instead, the area was merged into Oklahoma in 1907. Even so, the work done for Sequoia ended up shaping Oklahoma's final structure in lasting ways. On the East Coast, Delmarva nearly became real in 1833. The Delmarva Peninsula is split between Delaware, Maryland, and Virginia, but it feels like one continuous region. Delaware proposed unifying it into a single state. Maryland seriously considered the idea and even discussed letting residents decide. Most signs pointed toward approval, but when the final vote came, it failed by a single vote, 5-4. That was it. The vote decided that Delmarva would stay divided. It's probably one of the clearest, almost happened moments on this list. Back to the Civil War period, there's Nickajack. This proposed state would have covered parts of eastern Tennessee and northern Alabama. The region's terrain didn't favor large plantation agriculture, so, for obvious reasons, many residents didn't support the Confederacy. When their states aligned with it, locals tried to break away and remain aligned with the Union, similar to what West Virginia managed to do. But the political structure worked against them, and the plan never moved forward. Even so, many people in the region still chose to support the Union individually, showing how divided things were locally. Then you get Deseret, one of the most ambitious ideas on the list. In 1849, Mormon settlers proposed a massive new state centered in present-day Utah. It would have included large parts of what are now several western states. They didn't wait for approval. They wrote a constitution, set up leadership, and ran their own system for about 2 years. The proposal was simply too large and too complicated for Congress to accept. Instead, a smaller Utah territory was created in 1850. Still, the idea of Deseret didn't disappear immediately. It continued quietly in the background for years, almost like a parallel vision of what the region could have been. Next is Franklin, an early and surprisingly advanced attempt. In 1784, settlers in what is now eastern Tennessee felt abandoned after a confusing land situation. So they created their own state. They had a capital, a legislature, courts, and leadership under John Sevier. They even applied to become the 14th state, but fell just short of the required votes. For a few years, Franklin operated alongside North Carolina, almost like two parallel systems in the same place. Eventually, support faded, and the region was brought back under North Carolina's control, but not before proving how far a determined group could go. Even earlier, in 1776, there was Westsylvania. This proposal covered parts of modern West Virginia and western Pennsylvania. At the time, it wasn't even clear which colony controlled the area. Settlers felt stuck between distant authorities and wanted a system closer to home. They asked Congress to recognize them as a new state. Congress ignored the request, and once the border dispute between Virginia and Pennsylvania was settled, the idea lost momentum quickly. Without that uncertainty, the push for independence no longer had the same energy. And finally, Transylvania. Despite the name, it has nothing to do with Dracula. In 1775, a land company led by Richard Henderson bought territory from the Cherokee and tried to establish a new colony in what is now Kentucky and Tennessee. But the deal broke British rules about land ownership. Before anything could fully develop, Virginia stepped in, canceled the agreement, and took control of the land. It's one of the earliest examples of how complicated land claims were in early America. If you zoom out a bit, a pattern starts to show. A lot of these places were on the edges, far from where decisions were made, harder to reach, with their own way of life. And here's something you might have noticed. Tennessee keeps popping up. 4 out of these 12 lost states were connected to it in some way.
The prehistoric landmass Doggerland wasn't some empty wasteland during the last ice age, like scientists used to believe. It was alive, full of trees, animals, and maybe even people. And then the North Sea swallowed all of it like it never existed. So, no, Doggerland was not some ancient gigantic dog pound, although that would have been cool. It was a massive stretch of land that used to connect Great Britain to mainland Europe. You could have walked on it from modern-day England to the Netherlands without seeing water. Rivers cut through it. Animals migrated across it. And early humans likely followed those same routes, finding prey, gathering, and building their lives on this land. Then, glaciers melted and sea levels began to rise. Doggerland was drowning slowly. Land turned into wetlands, and wetlands broke into islands. Islands shrank year by year. Forest paths turned into marshes, and rivers widened into channels. And eventually, somewhere between 10,000 and 7,000 years ago, the sea finished the job. But now, scientists have pulled out evidence of a full forest ecosystem that existed here over 16,000 years ago, thousands of years earlier than previously thought. They used sedimentary ancient DNA analysis to figure it out. Every living thing leaves behind tiny traces of itself, microscopic fragments of DNA, and those fragments can get trapped in mud and sand. Over thousands of years, layers build up, and those fragments stay there, like fingerprints pressed into wet cement. Scientists drill down, pull up those layers, and read them like a timeline. When they analyzed sedimentary ancient DNA from 252 samples from 41 marine sediment cores, they found traces of oak trees, elm, hazel, real temperate forest species. And they weren't just surviving there, but thriving more than 16,000 years ago. That's deep into the last ice age, a time we've always imagined as brutal and lifeless, especially in northern Europe. But instead of a frozen desert, it looks like this area was a hidden pocket of life. And this wasn't just a temporary burst of life after the ice, but a deep-rooted ecosystem. It was stable enough to support large trees with massive root systems. You don't get that unless the soil holds together, unless there are seasons, growth cycles, and enough balance for life to settle in and stay. Among all the DNA, scientists found traces of a tree called Pterocarya, a distant cousin of modern walnut trees. The weird part is that researchers believed it disappeared from that region around 400,000 years ago. But somehow, it held on here, and that detail changes how we understand extinction. It could mean that species don't always vanish completely. Sometimes they retreat, hide, and survive in small pockets we just haven't discovered yet. All this means that parts of Doggerland probably remained above water during major flooding events, like the Stagega tsunami around 8,150 years ago. This means this land didn't just vanish, it resisted. It broke apart slowly, holding on in fragments before it finally disappeared. But actually, all of that still exists. It's not alive or visible, but preserved under layers of seabed and miles of seawater. Ships pass over it every day. Waves roll across it. If you could somehow drain the North Sea for a moment, you would see those old river channels carved into the earth, soil layers, and maybe even preserved roots where trees once stood. Another cool detail is that scientists think Doggerland might explain why traces of early humans in Britain seem so scattered. If people lived there, and it's very likely they did, then when the sea swallowed the land, it swallowed their history with it. Campsites, tools, pathways, and entire communities were all gone. Now, Doggerland isn't some one-time anomaly, so let's jump to the extreme opposite, Antarctica, with its endless ice, brutal winds, and temperatures that don't forgive anything. You look at it and think nothing survives here. But scientists walked across it and proved that idea completely wrong. Between late 2019 and early 2020, a team trucked across a remote part of Antarctica. Their instruments picked up something strange under their feet. Not solid ice as they expected, but something softer. So they drilled. Layer after layer of ice came out, until about 40 feet down, they hit something impossible: liquid water. It was a lake hidden under ice in one of the harshest environments on Earth. They tested the water, trying to understand where it came from. Because this place doesn't get much snowfall, the wind strips moisture away. Sunlight evaporates whatever little exists. So, how does a lake survive here? The answer is chemistry. Tiny traces of dissolved materials in the water help scientists find a hidden source. It turned out that a nearby glacier feeds the lake through underwater pathways no one knew existed. And then they looked closer and found microbial mats, living carpets made of microscopic organisms inside that dark sealed environment. Some stretch flat across the lake bed like rugs. Others grow upward in spiky shapes that rise up to about 15 inches tall. That's over a foot of life growing in total darkness, under thick ice, completely cut off from the outside world. And this life doesn't just exist, but organizes and changes over time. It's structured like a miniature forest floor, just in a completely unusual form. Another Antarctica discovery that shocked scientists was bubbles. They sit inside what might be the oldest ice ever brought up into daylight, nearly 1.2 million years old. Now, before this, researchers could only track Earth's climate history back about 800,000 years. That already felt ancient, but it still left a huge chunk of our planet's story missing. So scientists went looking for the right ice to fill in the gaps. Some parts of Antarctica actually hold ice that could be 3 or even 4 million years old, but it's messy and incomplete. They needed a clean timeline, layer after layer, year after year. So they spent years searching for that perfect spot, scanning the frozen continent like detectives looking for a buried archive. And when they finally drilled down into the ice at just the right location, they hit something special: crystal clear ice cores, stacked like a frozen timeline with tiny bubbles inside. Each one came with a microscopic sample of ancient air, sealed off from the world for hundreds of thousands, sometimes over 1 million years. When scientists study those bubbles, they can figure out what the atmosphere looked like, what gases filled the sky, how much carbon dioxide floated around, and how the planet's climate shifted over time. One moment locked inside that ice stands out more than most: the period around 900,000 years ago. That time might have been one of the closest calls our species ever faced. According to genetic studies, back then, the human population dropped to around 1,300 individuals worldwide. Nobody knows exactly what caused it, but climate is one of the biggest suspects. Massive environmental shifts, changing temperatures, unstable ecosystems, everything could have stacked against early humans at once. And those bubbles might hold clues to what kind of world those few survivors had to endure. So when scientists look inside one of those ancient bubbles, they're tracing survival. They're asking how a handful of humans made it through one of the toughest chapters in Earth's history, and what that might mean for us today. And when scientists scanned Antarctica from space, they found something even harder to wrap your head around. Beneath over 6,000 feet of ice, they detected an ancient landscape. Not rough shapes, but actual terrain with valleys carved by rivers and land split into blocks by tectonic forces millions of years ago. A place where water once flowed freely across the surface. This landscape dates back around 34 million years ago, to a time before Antarctica froze over completely. And somehow, in this one region, the ice didn't grind it away. It just sat on top of it, frozen in place, and preserved it like a time capsule. Scientists described it as a ghost, because it shouldn't still exist. Most landscapes get reshaped, erased, recycled by Earth over time, but this one just stayed. When you connect all of this, you can see that Earth doesn't change slowly and predictably. It hides things like entire ecosystems and histories. We walk around thinking we know this planet, but underneath us, under oceans and ice and layers of time, there are entire worlds we haven't even touched yet. Kilauea, one of the most active volcanoes in the world, erupted again in March 2026 on Hawaii's Big Island. Huge lava fountains shot into the sky. The main highway was closed, and the airport was blocked by sandpaper clouds of ash. The sky turned a creepy deep red. That's how thick the smoke was. The eruption literally closed some areas of the island. It was already the second time this year. The eruption happened right inside the Halimu'umu'u crater at the volcano summit. Things got dangerous fast, and visitors had to evacuate the volcano summit. The lava fountain shot straight up about 1,300 feet. That's almost as tall as the Empire State Building or higher than the Eiffel Tower. But let's watch the eruption unfold step by step. It started on March 10, 2026, and lasted about 9 hours, ending suddenly at 6:21 p.m. The eruption started in the morning at 9:17, with lava shooting up from the north vent. As for the south vent, it started erupting just before 10 a.m. By early afternoon, the lava fountains were huge. The south vent reached 1,150 feet high, and the north vent was 1,000 feet. The lava was flowing across about 1/3 of the crater floor, glowing bright orange and red. As the lava cooled in the air, it turned into something called tephra. That's a mix of volcanic rock, ash, and tiny glassy shards. Tephra can scratch your skin like sandpaper, making your eyes sting and making it hard to breathe. Even worse, it can turn roads into skating rinks for cars. Because all of this, part of Highway 11 was closed between mile markers 24 and 40. Back in January, during another eruption, it also rained tephra over the park and nearby towns. Some unlucky visitors actually got hit by falling tephra, and a few even got cuts. The Park Service had to close the summit for the first time since its eruption cycle began on December 23, 2024. Now, the National Weather Service says the eruption plume reached 25,000 feet high. That's nearly 5 miles straight up, higher than most airplanes fly. Winds were blowing from the south, so ash and gas started moving north from Halimu'umu'u. Officials warned people in nearby cities to stay indoors or leave if the gases began to bother them. Now, this eruption wasn't the first trouble Kilauea caused this year. An earlier one started on February 15th and lasted almost 10 hours. During that eruption, lava covered half of the crater floor. Scientists estimate that 15 million cubic yards of lava came out. That's enough to fill thousands of swimming pools or cover hundreds of football fields. At 2 p.m. on March 10th, tephra was still falling. Park rangers helped evacuate visitors from the summit. All trails and viewing spots near the summit were closed. Scientists are keeping an eye on things all day and night, watching how high the lava shoots, how fast it flows, which way the ash cloud is moving, and where the fallout spreads. Even though the lava mostly stays in the crater, tephra and volcanic gases can make living near a volcano pretty risky. Since December 24, 2024, Kilauea has been spitting lava on and off, mostly from 2 vents at the summit crater, one to the north, one to the south. Eruptions happen in short bursts, usually less than half a day. After that, the volcano takes a break for a while. Could we say the volcano is chilling? No, we can't. Sometimes those pauses can last 2 weeks or more, as if giving the lava time to catch its breath before the next show. But let's talk a little bit more about tephra. The biggest problem is that it doesn't just stay near the volcano. In past eruptions, it rained down on neighborhoods as far away as Hilo and Puna, messing up water systems and creating a huge cleanup job. At Hilo International Airport, all evening flights were canceled because of ash in the air. And for weeks afterward, locals and park staff were sweeping tephra off roofs, gutters, streets, just about everywhere you can imagine. According to the park spokesman, the reason tephra spread so far is a mix of weak winds and extremely tall lava fountains. When that happens, the volcanic debris drops straight down over the park and nearby towns. During past eruptions, steady winds, called trade winds, which usually blow from east to west across the islands, acted like a conveyor belt. They carried ash and volcanic gases over the Cow Desert and nearby towns to the southwest. Another super dangerous thing about an eruption is glass rain, also called Pele's hair. It's a kind of tephra that happens especially when lava fountains shoot up really fast. Tiny gas bubbles in the lava burst and stretch the molten rock into super thin, fragile strands. The wind then carries them far away. This stuff is lightweight but brittle, so it can scratch your skin or get in your eyes or lungs. The name comes from Pele, the Hawaiian goddess of fire and volcanoes, because it's kind of born straight from volcanic activity. During big eruptions, like the one in 2018, these strands were reported falling all around the volcano. Now, Kilauea isn't the only threat in the region. The sleeping giant next door, Mauna Loa, got an update from scientists on March 5, 2016. The volcano isn't erupting yet, but it's inflating as magma fills its huge underground chambers. You might think of it like Earth taking a deep breath. But it isn't just breathing. In the past month alone, over 100 earthquakes have been detected under the summit. Should we get worried? Well, let's figure it out. Mauna Loa, the largest active volcano on Earth, covers half of Hawaii's Big Island. Its eruptions can produce huge, fast-moving rivers of lava, like a slow-mo bulldozer made of molten rock moving across the area. When Mauna Loa erupts, it usually starts at the summit. From there, lava can flow into different areas: the Northeast Rift Zone, Southwest Rift Zone, or even vents on the northwest side of the volcano. The most intriguing thing is that these lava flows can appear within minutes, hours, or even months after the eruption begins. Since its first well-recorded eruption in 1843, Mauna Loa has erupted 34 times. The gaps between eruptions can range from just months to many decades. Its most recent eruption was in 2022. Right now, Mauna Loa is quiet but active. Seismic activity, that is, small earthquakes under the volcano, shows that magma is, in fact, moving beneath the surface. In February 2026, scientists detected 116 earthquakes beneath the summit, mostly gathered under the caldera era called Makuaweo Veo. Some were also concentrated in the southern caldera. But don't let this number scare you. For comparison, the month before had 123 earthquakes. The thing is, these quakes are part of the normal breathing of the volcano as it refills with magma after the 2022 eruption. GPS instruments on the volcano indeed show that the summit is inflating, meaning the ground is slowly rising as magma fills the underground reservoir. At the same time, gas and temperature readings from the Southwest Rift Zone are at normal levels, which means no major changes compared to previous months. So even though Mauna Loa is refilling, there's no immediate sign of a new eruption, yet. In any case, Mauna Loa is always worth watching. It's a sleeping giant that can wake at any time, and scientists are keeping a close eye on every inch of rising ground. Because if Mauna Loa erupts, it can cause a ton of different problems. Massive rivers of lava can flow quickly and cover land in their path. The volcano itself can also make the ground shake, because as magma fills it, the sides of the mountain can shift up or sideways, triggering earthquakes. On top of that, Mauna Loa can release volcanic gases that mix with the air and create fog, a kind of smog that can be irritating or even make it hard to breathe for people living downwind. Sometimes, the volcano might even produce small explosions, sending ash into the sky, which can be dangerous for airplanes flying nearby.
The shipwreck of the MS Estonia is one of the most horrible maritime disasters in Europe. The wreckage of this giant ship still lies on the bottom of the Baltic Sea, but for a long time the authorities didn't allow anyone to approach it. Moreover, they even once planned to bury the vessel under thousands of tons of concrete. But why? It was just a passenger ferry. Perhaps someone really wanted to hide some secret connected with the ship. Let's try to figure it out. On September 27, 1994, MS Estonia departed from Tallinn for a routine trip to Stockholm. There were 803 passengers and 186 crew members on board. From the very beginning of the journey, the ferry encountered difficulties in the form of a powerful storm. However, high waves and strong winds weren't unusual for the Baltic Sea in autumn. And of course, the crew was prepared for that. But around 1 a.m., something went wrong. A loud metallic crash was heard. According to the later accident report, this noise was caused by a giant wave striking the ship. But there was something unusual about that wave. You'll learn about it a little later. So a loud crash rang out. Then around 1:15 a.m., the ship's bow visor lifted. Its doors burst open and water rushed into the vessel. The crew sent a distress signal, but the water was filling the ship too quickly. Around 1:50 a.m., Estonia sank. Out of all the passengers, 138 people survived. One of them later passed away in the hospital. News of the disaster shocked Europe. For Sweden and Estonia, it was one of the greatest catastrophes in the history of both countries, since most of the passengers on board were citizens of these nations. But what exactly happened there? Why did the ship sink so quickly? What was that huge wave? Of course, an investigation began. At first, it raised no questions, but later, something strange started to happen. Estonia, Sweden, and Finland organized the Joint Accident Investigation Commission, or JAIC. After a thorough investigation, the commission concluded that the bow visor's locking mechanism failed under the pressure of heavy seas, causing the visor to detach, tearing the bow ramp open and allowing massive amounts of water to flood the car deck. But why did this happen? The cause was said to be poor maintenance. However, survivors said that everything began with a loud crash. The locks couldn't have created such a sound, which means something else must have happened. Moreover, people didn't just hear some kind of explosion, they actually felt it. But for some reason, these witness statements weren't included in the report at all. Strange, right? But that was only the beginning. When a ferry is in port, its watertight bow visor opens so that passengers and vehicles can board. This section opened during the storm and allowed water to rush inside. However, the bow visor was later found about 1 mile away from the site of the shipwreck. 6 weeks after the disaster, it was lifted from the seabed and hidden at a base near Stockholm to conduct a thorough investigation. This piece of the ship remains there to this day. The Swedish authorities promised that they would raise the entire ship from the seabed, but then something happened, and they suddenly changed their minds. Then, in 1995, the governments of Sweden, Finland, Estonia, the United Kingdom, and several other countries banned any research into the wreckage altogether. As punishment, offenders could face 2 years in prison. They said it was for ethical reasons. According to them, the site is a maritime grave and therefore no one should approach it out of respect for those who drowned. But the strange decision didn't end there. The authorities of Sweden, Finland, and Estonia even decided to seal the sunken ship in concrete so that no one could disturb the wreckage or allow grave robbers to reach it. Of course, the relatives of the passengers were outraged. They held meetings and demonstrations, protested against the decision, and it worked. The authorities abandoned the plan to seal the ship in concrete, but the ban on unauthorized approach is still in effect. Immediately after the strange investigation and the statements from officials, people began talking about conspiracy theories. Perhaps the ship had been transporting some kind of secret technology or sensitive information. Considering that this hypothetical technology was being carried on a passenger vessel, someone may have wanted to keep that transport secret. Another version claimed that some kind of underwater rocket struck the ship. It pierced the bow section and created the loud crash that survivors heard. But why would someone launch such a rocket? Perhaps because of the ship's secret cargo. Even if the vessel was carrying something classified, is there any evidence pointing to this version besides theories? Yes, there are a few. In 2000, a German journalist managed to reach the wreck site and took a sample from the hull of the sunken ship. He analyzed this piece and said the metal had been subjected to forces caused by an explosion. However, other specialists from a government laboratory later discovered that similar marks could be found on other ferries as well. They said this wasn't the consequence of an explosion, but the result of a special anti-corrosion treatment applied to the steel. It's difficult to say what to believe, but there was another detail. In 2004, 10 years after the tragedy, Swedish television interviewed a former customs officer who had worked at the port of Stockholm. He said that a few weeks before the disaster, 2 boxes had been transported through the port aboard MS Estonia. The customs officer wanted to learn more about the cargo, but his superiors ordered him to ignore it. That means the ship perhaps had already been transporting some kind of secret cargo even before the tragedy. The ban on researching the wreckage, witness statements that were not included in the investigation, the customs officer's interview, and the public outrage, all of these factors were too significant to simply ignore and forget about the disaster. Despite the authorities' ban on approaching the ship, one man decided to do exactly that. Swedish journalist and filmmaker Henrik Evertsson sent down a camera attached to a machine that can swim underwater and carefully examined the wreckage of MS Estonia. In 2020, he released a documentary film about it, and of course, the film revealed many things that the authorities had never talked about. The director's team used a remotely operated underwater vehicle that descended to the seabed and filmed the ship. They discovered a large hole on the starboard side of MS Estonia. The filmmakers stated that such damage couldn't have been caused by waves, by the detached bow, or by the seabed. If the ship had struck rocks, it might have been believable, but according to the director, the wreck site consisted of deep, soft clay. They concluded that such a hole in the hull could have been caused by an object the size of a small submarine that collided with the ferry at high speed. Of course, this film couldn't be ignored by the authorities. They admitted that a new investigation had to be conducted. During 2021 and 2022, the authorities of Estonia, Finland, and Sweden organized several dives to the wreck site. They used special cameras, 3D laser scanners, and other advanced equipment. Then, an interim report in 2023. They stated that there were no signs of a collision between the ship and another object, and no evidence of any explosion in the bow section. It was also reported that the vessel had been unseaworthy at the time of its final departure because of technical defects. Henrik Evertsson was arrested for illegally exploring the wreckage, but fortunately, he didn't receive a prison sentence. Instead, he was ordered to pay fines. In 2023, a television documentary about Evertsson's work was released. The film claimed that Henrik wanted to convince the audience that an unknown object had collided with the ship and used graphic materials that misled viewers. Perhaps he didn't do that. Perhaps the authorities were right. Or perhaps the conspiracy theories surrounding the ship are also true. To this day, no one knows exactly what happened to the MS Estonia on that ill-fated day.
Sea levels. Sea levels.
The glaciers are melting.
Sea levels are rising almost everywhere on Earth. Beaches are shrinking and coastlines are prepping for trouble, but not in Greenland. Ironically, the same giant ice sheet that can flood the planet could also make parts of Greenland rise out of the ocean by the end of this century. What kind of physics glitch is this? The answer starts with the weight of ice. Greenland is buried under a ridiculous amount of ice. It covers about 80% of the island and spreads across roughly 660,000 square miles, about 3 times the size of Texas. In some places, it's more than a mile thick. At its deepest, it's close to 2 miles. If all of it melted, global sea levels would jump by about 23 feet. Coastal cities like Miami Beach would stop looking like vacation spots and start looking like tourist attractions for divers. And underneath all that ice is actually land. Greenland is not a floating iceberg. It's a real island with mountains, valleys, and rivers. For ages, all that ice has been pressing down on Earth's crust like a giant thumb pushing into soft ground. The crust isn't completely stiff. It sits on top of deeper rock that can slowly change shape over time. The enormous weight of the ice has depressed parts of Greenland's crust, and some bedrock beneath the ice now lies below sea level. Basically, the weight of the ice has made the island sag a bit. But now the island is losing ice relatively fast. Every year, hundreds of billions of tons end up in the ocean. When you lift something heavy off the ground, the Earth starts to push back up to where it was before. Greenland works in a similar way. As the ice melts away, the land underneath starts to bounce back up like a spring that's been squished. Everything with mass has gravity. Planets have it, moons have it, skyscrapers and mountains have it. Your house has it, your coffee mug too, even you and me. But it's so small it's basically impossible to measure. However, Greenland's gravity, even though small, acts like a magnet for the nearby ocean. It pulls the water right toward its shores. That nudge is tiny but still makes a difference. So when Greenland starts to lose its mass, the gravitational grip will weaken. This makes the water slosh away into the open ocean. Scientists already theorized Greenland would bounce back as it shed ice, but new research shows that some of the rebound might happen faster. The secret could be buried deep underground. Rocks way down could be helping to lift the land, meaning this isn't a slow change that's going to happen ages from now. Some coastlines might keep rising throughout this century, with the biggest shifts likely happening by 2100. In some parts of Greenland, scientists think the land could actually go up by a few feet over the next few generations, which is pretty significant when you consider how things move in geological terms. One reason southeast Greenland stands out is its weird geological history. Millions of years ago, this part of the island passed over the Iceland Plume, a deep upswelling of superheated rock. That ancient heat may have left the upper mantle weaker than usual, which could explain why uplift there is happening faster than scientists expected. Underneath all that ice, Greenland has some surprising secrets. Scientists have discovered a huge canyon buried beneath the ice sheet that's 460 miles long, way longer than the Grand Canyon. This ravine is hidden in complete darkness below the frozen surface, but subglacial rivers are still going through it, carrying meltwater out to the Arctic Ocean. Researchers have even pulled up drill cores that show ancient soil and plant remains. It turns out that millions of years ago, this frozen island was actually green and covered in vegetation. The melting ice is even exposing a top-secret ghost town. Back in the 60s, the military built a hidden base powered by a nuclear reactor straight into the ice sheet. The project was called Project Iceworm, which aimed to test whether nuclear missiles could be hidden under the ice. Scientists assumed the ice was stable, but the moving ice quickly crushed and warped the tunnels, forcing them to shut down. They thought it would stay safely buried forever, but now, thanks to the shrinking glacier, those abandoned tunnels and heavy machinery are slowly coming right back up to the surface. The melting ice triggers another cool chain reaction. Moving billions of tons of water off the island shifts the weight across the entire globe. But most of that mass heads towards the equator. When Earth gets heavier around the middle, its rotation slows down. It works kinda like a spinning ice skater stretching their arms out. The entire planet actually takes longer to complete a full spin. Yes, the melting ice is actually making a day longer. The actual shape of the planet changes along with it. Earth is already slightly lumpy rather than a perfect sphere. The sheer mass of the Greenland ice sheet helps warp the crust. As the ice melts and the ground bounces back, the physical geometry of the globe shifts. So not only does it make the day longer, it can actually bend the world out of shape, literally. Back on the surface, the consequences get very local very fast. Greenland's towns are mostly built along the coast, and many depend on fishing. But when the land rises, the water near the shore gets shallower, harbors can turn muddy, ships can get stuck, and towns may need to dredge channels just to keep supplies moving. The coastline also starts changing shape. New rocks and small islands can appear, and routes that used to be safe can suddenly become risky. And the ice sheet itself is anything but quiet. Huge outlet glaciers like Helheim keep pushing toward the ocean, cracking and grinding as they go. When giant slabs break off and crash into the sea, the impact can be strong enough to trigger glacial earthquakes. Those shockwaves travel through the planet, and seismographs thousands of miles away can pick them up. At the same time, meltwater can slip underneath the ice and make the whole glacier slide faster, like a heavy object suddenly hitting a wet floor. Once meltwater starts moving through the cracks in the ice, it can weaken the glacier from above and below at the same time. The shifting landscape can trigger even bigger chaos. In 2023, part of the mountain in East Greenland collapsed into a narrow fjord and launched a wave about 650 feet tall near the impact. The walls of the fjord trapped the water, turning the whole place into a giant sloshing basin. The water sloshed back and forth so violently that the entire planet vibrated for 9 straight days. Another interesting thing is that the snow on top is messing things up for the ice underneath. When it gets warmer, tiny algae start blooming like crazy and turn the snow pink. Locals call it watermelon snow. It might sound cute, but it's a big problem. Bright white snow reflects sunlight really well, but when it turns pink, it starts soaking up heat like a dark shirt on a hot day, which makes it melt way faster. The ice also gets covered with tiny particles like dust, soot, and microbes. Because they are darker than clean ice, they absorb more sunlight and melt little pits into the surface. Millions of these tiny pits can turn the solid surface into something like frozen Swiss cheese. Scientists call them cryoconite holes. They form when dust, soot, microbes, and organic material clump into dark grains that absorb sunlight, melting narrow little shafts that can even host tiny microbial ecosystems inside the ice. And that's what makes Greenland so fascinating. At the start, this looks like a physics glitch. An island losing ice should mean more water and higher seas. But Greenland doesn't play by one simple rule. As the ice shrinks, the land rises, the nearby ocean shifts, and deep rock starts responding too. What looked like a contradiction is really a whole chain reaction hiding inside one frozen island.
This is Thwaites Glacier located in West Antarctica. It's also known as the Doomsday Glacier because if it collapses, it's game over for coastal cities. While summers are getting hotter, the glacier is being eaten from below by warm currents. It looks bad, but scientists have a plan. They consider building a gigantic sea curtain, an underwater 50-mile-long wall chained to the bottom of the dark ocean floor of Antarctica. Is this even possible, and will it work? Let's find out. The Doomsday Glacier is roughly the size of Florida. It's a massive river of ice draining a huge chunk of West Antarctica into the ocean. It currently loses more than 50 billion tons of ice every year. That equals 20 million Olympic swimming pools of water being pumped into the global sea. This single glacier causes about 4% of global sea level rise each year. This number might sound very, very small, but that melt rate is accelerating. If Thwaites crumbles completely, it holds enough water to push the global ocean up by a full 2 feet. It would permanently erase beaches and turn daily high tides into neighborhood floods. That's 2 feet added permanently to every high tide, every storm surge, every coastal flood, everywhere. But the real danger isn't the 2 feet. Thwaites helps hold back enormous volumes of inland ice. If it goes away, much more of West Antarctica can follow, leading to the sea levels rising far more than just 2 feet. To prevent this, engineers modeled the most ambitious underwater megastructure in human history. Satellites can see the surface, but the real problem is below the glacier. Near Thwaites, there's warm water. Even water that's only a few degrees above freezing can melt ice if it keeps flowing. It's like holding an ice cube under a running faucet. The water doesn't need to be hot, it just needs to keep coming. Over time, water thins out the glacier from beneath and weakens the brace holding it back. Once that brace gets weaker, the ice loses its grip on the seafloor and slides into the deep ocean much faster. That's where the sea curtain idea comes in. The goal is to keep that warm, deep water from reaching the underside of the ice shelf in the first place. Something like a long, flexible underwater barrier that rises up from the seafloor and blocks the warmest water from sneaking underneath. It doesn't fix the glacier forever, it just buys time by cutting off some of the ocean heat. So, how do you build something like that? Don't imagine a massive concrete dam. It looks more like a long underwater shower curtain, stretching 50 miles and 500 feet tall. Along that line, anchors are planted into the seafloor like underwater tent stakes, and overlapping flexible panels are attached, so they can bend instead of snap. Warm water is saltier, which makes it heavier, so it sinks and slides along the bottom, creeping under the ice shelf from below. The curtain rises high enough to block that deep layer. When the warm water reaches it, it has to move upward and mix with colder water, which cools it down before it can melt the ice as effectively. Human construction crews cannot dive 3,000 feet.
pressure is unbearable and even sunlight doesn't care about going that deep. Building the curtain requires a fleet of autonomous underwater drones. These robots will use sonar to map the terrain before drilling massive steel anchors directly into the bedrock. Once the curtain is up, they'll patrol the line looking for rips. Living at the bottom of the world would need some serious setups. Those robots can't just swim up to the surface to change batteries. The freezing ocean above would lock them into place. To make this work, engineers might have to set up a whole underwater base camp. Drones would probably have to dock at huge charging stations on the ocean floor just to recharge for their next mission. The ocean itself will work against this project. The strong currents and drifting icebergs would always stress the curtain. In those conditions, the concrete wall would break. That's why they're looking at using flexible fibers. It bends and wobbles with the flow. If a random current makes a little tear, the current just flaps until a robot shows up to fix it. Engineers also have to worry about rogue icebergs. When massive chunks of the glacier break off, they rarely float away cleanly on the surface. Getting the gear to this part of the world is already an epic quest. Antarctica doesn't have a Home Depot yet. So bolts, fiber, and spare drones have to arrive on cargo ships from thousands of miles away. The team only gets a brief summer window to work before the ocean surface freezes completely solid. But even if engineers could achieve all of this, there's one other roadblock to consider before putting up a roadblock in the water. The Southern Ocean carries nutrients for tiny floating plants called phytoplankton. When plankton blooms, it feeds krill. Krill feeds fish and squid, and they are food for lovely penguins, seals, seabirds, and even whales. What if the current accidentally sends that heat straight into a different glacier, or blocks food from reaching local whales? You cannot exactly test a project this massive in a local swimming pool. Building this underwater marvel is only step one. It requires a permanent mechanical workforce living down there for decades to swap out cables. Experts estimate that the project could cost around $80 billion. That is literally space program money. The hardest part of the entire project might actually be getting coastal countries to split the massive bill. The most likely funding model would be a coalition of coastal countries because they don't want their cities turned into aquariums. But even a perfect 50-mile underwater curtain cannot completely stop the ocean from rising. It only hits the brakes on one specific problem. The ocean actually rises in a few different ways all at once. Surprisingly, not all of them involve melting ice. When water gets warmer, it actually expands. The molecules in the water get super active and spread out more. That means the same amount of water now takes up more space. And because the ocean has nowhere else to go, that extra volume pushes the surface higher. The planet is doing exactly this, but on a much bigger scale. Then, we have Greenland. It's way bigger than glaciers like the Doomsday Thwaites. It's a sheet of ice the size of an entire country. The Greenland ice sheet has been shrinking for decades, with net ice loss every year for nearly 30 years straight. If that block melted completely, global sea levels would rise by 23 feet. That can put a two-story house completely underwater. Mountain glaciers also add to the global sea level. Alaska alone has thousands of these, let alone what is scattered around the world. These mountaintops act like giant frozen water towers. They're slowly dripping away under the sun and feeding into the same global sea. Combine all that extra water with a storm surge and the results get very real. A storm surge acts like a giant shovel, pushing the ocean inland for a few hours. If the starting water level is even 1 inch higher, that surge pushes significantly further down your local streets. It easily overtops concrete seawalls that used to do the job perfectly. This can lead to a rare neighborhood flood suddenly becoming a yearly headache. None of this means you should cancel a trip to Miami, not in this century. Sea level rise is slow, and even a Thwaites collapse would likely play out across decades. But it's still moving in the wrong direction, which is why scientists are hunting for ways to slow the clock. And honestly, if this curtain ever gets built, watching robots anchor it to the Antarctic seafloor would be one of the strangest engineering live streams in history. Deep inside an icy cave in Romania, scientists drilled out a 5,000-year-old layer of ice. Inside, a cold-loving bacterium was sleeping. It came back to life and shrugged off some of our strongest antibiotics. So if ice can preserve something like that, are we in danger as the planet warms and more old ice starts melting? Ice is like a library that files winters. Every new snowfall or drip of water that freezes adds a fresh layer. Scientists can slice through those layers to see what was blowing in the wind at the time. They find trapped dust, old pollen, or even stray microbes. The polar ice sheets are the biggest library of this kind on Earth, with books that stretch back over 800,000 years. But you do not have to travel to the Antarctic to find ancient ice. The planet has plenty of hidden underground freezers. One of the largest is the Scara Shoara ice cave in Romania. Tucked deep inside a limestone mountain, this cavern holds over 3.5 million cubic feet of solid ice. Getting down there is an adventure. Researchers descend a steep metal staircase about 160 feet into the cave. Standing on the frozen floor, they use hollow drills to carve out giant tubes of ice. Once, they pulled out a single core roughly 83 feet long, or about the height of an 8-story building. That ice dated back 13,000 years, long before human civilization. But the real surprise was the bacterium they found trapped inside. Bacteria are single tiny cells, basically microscopic bags of chemical reactions. They multiply by copying their DNA and splitting in half. This is a process called binary fission. If conditions are right, they can double their numbers in 20 minutes flat. Most bacteria that can infect us like it warm. Around 98.6 degrees Fahrenheit is their comfort zone, but the one from the Romanian cave belongs to a different kind. The name is foreboding, Psychrobacter. But don't worry, that only means it prefers cold temperatures. It does best in cold, fridge-like temperatures. Our body would be like a sauna for it, but that doesn't mean it's harmless to us. Ice preserves things by hitting the absolute pause button. Deprived of liquid water, the chemical reactions that normally break a cell down come to a complete halt. As long as the deep freeze keeps the cell intact, the germ can survive on standby for millennia. But give it some warmth and fresh nutrients in the lab and it wakes right back up. Scientists tested this strain against 28 antibiotics. It resisted 10 of them. The other 18 still worked, at least to some degree. But 10 failures out of 28 are enough to make scientists pay attention. Then they looked at its DNA. Inside, they found over 100 genes linked to antibiotic resistance, along with almost 600 genes we don't fully understand yet. There's also an important detail. Because this bacterium isn't common, scientists had to compare its behavior with that of similar species. So the resistance is real, but we cannot directly translate it into this is what would happen in a hospital. In lab experiments, the tiny germ showed it could actively interfere with other microbes. Researchers identified 11 specific genes in its DNA that are linked to producing compounds that may suppress or inhibit bacteria, fungi, and possibly even viruses. In simple terms, it's like a small soldier wearing armor. That's antibiotic resistance, but it also carries a few spray cans in its backpack that can damage other microbes. That's not unusual in nature. Microbes constantly compete, and many survive by making molecules that harm their rivals. That's actually how many of our antibiotics were discovered in the first place. So this strain carries two important traits. It can tolerate some antibiotics, and it may produce its own antimicrobial compounds. That combination doesn't make it some unstoppable organism that can eliminate the human race. But it does mean it carries biological tools that had evolved long before humans started making medicine. Here's what makes bacteria like this potentially problematic. Not because it can sprint into your bloodstream and establish a new colony there. It's not built for human body heat. The real headache comes from how bacteria behave around each other. They actively trade genetic upgrades, not like football players trading jerseys. More like coaches exchanging playbooks and learning new tactics. Bacteria pass around tiny DNA rings called plasmids, which contain bonus survival instructions. Other times, germs simply pick up loose genetic code from their surroundings, like finding a dropped wallet. The bottom line? We don't want these antibiotic genes to somehow end up inside a modern bacterium that thrives in humans. Creating a supergerm takes a wildly unlucky chain of events. The ancient germ has to meet a modern one to hand over its DNA. Then the new host has to actually assimilate it. Most of the time, that process fails, but the planet getting warmer could change how often these accidental meetups happen. More mixing means more chances for those upgrades. And we don't have to guess how thaw can cause trouble, because we've already seen a real-world example. In 2016, a heat wave hit the Yamal Peninsula in Siberia, with reports of temperatures around 95 degrees Fahrenheit, which is basically beach weather for a place that's supposed to stay frozen. Soon after, an anthrax outbreak showed up in local reindeer, and there were human infections too. Anthrax is a disease caused by a bacterium called Bacillus anthracis. This bacterium has a survival trick. When conditions get tough, it can turn into a spore. It enters sleep mode and stays like that for decades. The heat helped thaw and disturbed ground that had kept those spores sealed off, and once grazing animals ran into them, the whole cycle started up again. But bacteria aren't the only microbes that cold can preserve. Viruses can make it through too. Scientists have actually pulled ancient giant viruses out of Siberian permafrost. They earned that name for a very literal reason. Normal viruses are so incredibly tiny that you need a highly advanced electron microscope just to see a blurry outline. Giant viruses are huge in comparison. They are physically larger than some bacteria. You could easily spot them using a basic high school microscope, and after 30,000 years inside a cube of ice, researchers successfully revived them. The viruses immediately invaded living cells and started making copies of themselves. To play it safe, the team used simple amoebas as test dummies instead of human cells. But if this can be done with a virus so old, could there be other viruses in permafrost? Maybe something that targets animals or even humans? The short answer is precisely that. Maybe. But hold on, there's no need for a bunker just yet. Viruses are biological specialists. They're extremely picky eaters. To infect a cell, a virus has to latch onto the outside like a key fitting into a lock. A virus designed to infect a woolly mammoth or a prehistoric amoeba probably has the wrong key for a human cell. Our biology is just different enough that the door stays locked. That said, we aren't totally in the clear. Scientists have found genetic traces of things we do know, like the 1918 Spanish flu and even smallpox, preserved in permafrost and frozen remains. But finding broken pieces of genetic code is very different from finding a fully functional virus that can boot up and start an infection. Most of the time, age and background radiation turn these things into harmless leftovers. The realistic threat is not an apocalyptic zombie plague. It's an ecosystem disruption. If massive amounts of ancient microbes flood the ocean, they might mess up the bottom of the food chain, knock out a specific plankton, and starving fish create a ripple effect that hits bigger animals. Melting ice is a slow-motion issue that plays out over centuries. Science and medicine are wide awake and watching. Humanity already has plenty of daily troubles, so prehistoric germs belong near the bottom of your worry list. All the way back in 1972, a super-secret satellite was zipping around the globe. It was taking high-altitude photos of the flat grasslands in Kazakhstan. They were probably looking for military secrets. Instead, they caught a couple of frames of massive geometric shapes stamped into the dirt. They had accidentally photographed a 36-century-old ghost town. Because those photos were secret, it took decades for researchers to finally access the coordinates and send modern drones to map the area. That's how they uncovered a 346-acre ancient settlement. But what raised eyebrows isn't how big it was. The cool part is the high-tech prehistoric factory run by nomads. The site is called Semiyarka, which means the city of 7 ravines. Scientists named it like that because it's located on a cliff overlooking a wide river valley. It dates back to roughly 1600 BCE. At that time, the Eurasian steppe was basically a 5,000-mile flat belt of grass. The people living there were the ultimate minimalist campers. In this part of the world, large-scale farming is hard. Not impossible, just incredibly hard. It's much easier to befriend cattle and move when they're running out of food. Basically, nomads relied completely on herds of sheep and horses to survive. But if you keep a massive herd in one spot, they will chew the grass down to the dirt eventually. That gave humans a simple choice. Strap everything you own on an animal and follow fresh grass. Their food came straight from the animals as well. They lived on meat and fermented mare's milk, a sour, slightly alcoholic drink created by allowing horse milk to ferment in leather bags. But for some reason, builders in Semiyarka decided to stay. They settled on that cliff to build a heavy manufacturing plant right in the middle of the Bronze Age. It's when humans finally stopped hitting things with rocks and started melting metal. Bronze is not a single metal, it's a mix. The most useful kind was often copper mixed with tin, because that mix makes tools harder and helps them keep an edge. The timeline of technological progress around the world is almost random. While the residents of Semiyarka were firing up their metal ovens, the Egyptian pyramids had already been standing for 1,000 years. So what did the Semiyarka factory actually look like? We are way too early in the timeline for conveyor belts and brick chimneys. A Bronze Age metal shop was basically an outdoor dirt lot. It was noisy and covered in soot. It's fair to assume it smelled terrible. Charcoal smoke, burnt wood, melted metal. Probably not that different from a modern factory without AC. If we could take a walking tour, we would see scorched ground and broken clay everywhere. Workers kept all that loud work confined to the southeastern edge of town. They were highly organized. Archaeologists are certain this was a dedicated factory because they found 2 very specific things: crucibles and slag. A crucible is a heavy-duty clay cup specifically designed to survive sitting inside a 2,000-degree fire. Slag is the ugly, glassy garbage left behind after you pull the useful metal out of a rock. You cannot make slag by accident. It only forms when you intentionally melt metals. But what were they making here? Creating bronze was the ultimate survival upgrade for that time period. If you try to chop down a tree with a pure copper axe, the blade will bend like a cheap spoon. You'll have to stop, put the axe on a rock, and hammer it flat again. By adding a little bit of tin causes a chemical reaction that locks the metal atoms in place. The final product is incredibly hard. Many of the passing nomads drove massive wooden wagons roughly the size of a modern mobile home. They had solid wood wheels and required teams of oxen to pull them. Maintaining those giant wagons required sturdy tools, making Semiyarka the ultimate highway pit stop. They were mixing around 12% tin into their copper. Tin is a soft, silvery metal that melts at surprisingly low temperatures and acts as a heavy-duty chemical hardener when stirred into a vat of boiling copper. In the ancient world, tin was incredibly hard to find. Copper is fairly common, but entire empires would panic if their tin supply chain broke down because you cannot make bronze without it. Semiyarka was sitting on a local gold mine. They had access to tin in the nearby mountains, which could mean they controlled the exact ingredient everyone on a 5,000-mile steppe desperately needed. But what happened, and how did it end up a ghost town? We know for a fact they were not defeated by some other nomadic tribe or an army. Something like that would leave a very obvious dirt crime scene, from skeletons to a massive layer of black ash where stuff was burned down. There would be dropped weapons, those made on site. Semiyarka has none of that. Instead, archaeologists found a clean exit. The locals packed up their valuable tools, gathered their herds, and did what nomad tribes do. They moved on. At least we assume so for now. It's possible that they accidentally destroyed their own neighborhood. To keep an oven hot enough so it can melt metal, you need a lot of wood, which means they probably chopped down every single tree for miles. Without tree roots to hold the dirt together, the soil turns to dust. The grazing grass disappears. When it happens, traveling customers stop showing up. The town essentially turned its own front yard into a barren wasteland just to keep the factory fires burning. This whole domino reaction would leave clues, but the news is pretty fresh, so we might learn more soon. Semillarka probably simply faded away. It's certainly not the only advanced settlement that ended up lost in time. On the vast, empty steppe of the Ural, there's a city planned like a fortress from day one. That's Arkheim. It was another unexpectedly advanced place for this time. From above, the enclosing wall forms an almost perfect circle, about 520 feet across. Concentric walls ring the site, with a defensive ditch outside. Inside, roughly 60 houses curve along the walls like puzzle pieces. The layout shows careful planning and a well-organized community. Then there is Akrotiri. This Bronze Age town on the island of Santorini was buried by a massive volcanic eruption. The falling ash acted like concrete and actually locked the entire city in a perfectly preserved time capsule. Excavators found multi-story houses stacked on top of each other. You can still see vibrant paintings of ships and dolphins glowing on the walls. Inside the homes, water once ran through indoor terracotta pipes long before modern plumbing existed. There is also Derinkuyu in central Turkey. We only know it existed because of a home renovation gone wrong. Back in 1963, a local man took a sledgehammer to a wall in his basement. The wall crumbled and revealed a dark tunnel. He walked inside and accidentally discovered an 18-story underground doomsday bunker. It was a massive labyrinth carved out of soft rock, designed to hide 20,000 people. They even carved 1,000-pound solid stone wheels that they could roll across the hallways to seal the doors and block invaders. If you like Lord of the Rings, this has to remind you of dwarves and how they lived. One of the coolest things about modern tech is that it lets us map ancient places almost perfectly. Satellites and remote sensing tools can scan the surface of Earth and trace walls, streets, and workshops that have been buried for thousands of years. Once we have that map, we can rebuild the site digitally and even walk through it in a virtual model. It's not the same as standing on the steppe and melting bronze in open air, but it's the closest we get to stepping back in time. There are still countless vanished hubs waiting to show up on the next scan. Who knows what your neighborhood will look like in 3,600 years? Scientists just found out that the Earth's crust beneath the Marmara Sea is sending seismic signals that look exactly like the kind that show up before a major earthquake. An earthquake that can shake entire coastlines and send waves racing toward crowded cities. For years, scientists focused on visible ruptures on land because they could measure and map them easily. But now, they made a detailed map of a huge fault system under the seafloor. The Mediterranean already sits at a dangerous crossroads where massive tectonic plates meet. Those plates push, scrape, and stretch against each other, and that constant motion creates massive stress. The crust there grows thinner over time, and thinner crust means it can't absorb stress easily. Stress builds, pressure mounts, and the signals coming from below show that parts of this fault system have started to move in unusual ways. The new map shows that future large earthquakes may begin at the boundaries where weaker and stronger sections of the crust meet, or along edges of highly resistive zones. They even pinpointed one of the most likely locations, beneath the Marmara Sea. What makes this discovery so intense is the scale. The faults in the seabed form long corridors where energy can accumulate for decades or centuries. Scientists warn that this setup is the kind that can produce a super earthquake, a massive seismic event capable of shaking large coastal cities and possibly generating tsunamis. A tsunami forms when the seafloor shifts vertically and displaces huge amounts of water, so it looks really plausible in this setting. The water it sets free radiates outward in powerful waves that can cross entire seas. The Mediterranean holds dozens of densely populated shorelines, so it could affect millions of lives. Speaking of that, Let's zoom in on Istanbul, Turkey's largest and most populous city. The massive fault line sitting right under it doesn't act the way scientists thought it did. For years, experts looked at the main Marmara Fault, a branch of the North Anatolian Fault running beneath the Sea of Marmara, and worried it might rip in one single monstrous rupture. That kind of break could unleash a megaquake in the high 7s or beyond. But when scientists ran detailed computer simulations covering more than 10,000 years of earthquake cycles, they saw something different. The fault doesn't behave like one giant zipper waiting to unzip all at once. It behaves more like a row of connected tiles that break in sections. And the reason comes down to what's happening miles below the seafloor. It's called rheology. Simply put, how materials deform under stress, how rocks bend, stretch, or snap when you squeeze them hard enough. Under the central Sea of Marmara, giant piles of compacted mud, sand, and debris sit on top of warmer crust. In those upper layers, the sediment usually deforms slowly and steadily, especially at shallow depths where pressure and heat interact in specific ways. Deeper down, higher temperatures weaken the rocks. Warm rock flows more easily than cold rock. That heat acts like a built-in brake system that limits how far a rupture can tear through the crust. When researchers built a 3D earthquake cycle model, they fed in real heat flow measurements, rock friction data, and structural details, and replayed thousands of years of seismic activity. When they included both sediment thickness and temperature differences, the model finally matched history, including the powerful quakes of 1766 and 1912. And none of the simulated events exceeded magnitude 7.3. That level of shaking can collapse buildings, fracture infrastructure, and cause landslides. But it differs from the nightmare scenario of one continuous coast-to-coast rupture. Instead, different sections behave in different ways. The western segments produce more regular earthquakes, including magnitude 7.2 events roughly every 150 years. The eastern sections generate smaller double quakes, back-to-back events between magnitude 6.2 and 6.8 about every century, and a magnitude 7.0 roughly every 500 years. Parts of the fault don't snap at all, but creep. Scientists call it shallow creep, which just means the fault slowly slides without producing a major quake. It releases tension quietly, like letting air out of a balloon instead of popping it. GPS measurements and clusters of repeating small quakes over the past 20 years confirm that slow slip near the central basin. So what does this mean for Istanbul, a city of over 15 million people sitting practically on top of this system? A magnitude 7 or 7.3 quake close to the city could still rock neighborhoods, especially if two strong events strike in quick succession. Infrastructure, older buildings, and densely packed districts are at the highest risk. The fault hasn't produced a major rupture in this section since 1894, which means there's more than 130 years of accumulated strain. The simulations show major events could strike in the coming decades. Then there's Santorini, where more than 28,000 earthquakes happened in just a few months in early 2025. Most of the quakes stayed small, but some reached magnitude 5, strong enough to fracture walls, rattle nerves, and push authorities to close schools and evacuate parts of the island. And this wasn't just tectonic plates grinding like they usually do. This swarm moved. The epicenters shifted gradually northeast toward the Colombo submarine volcano about 5 miles offshore. That migration told scientists magma was on the move. Researchers calculated that roughly 80 billion gallons of it, enough to fill about 120,000 Olympic swimming pools, surged upward from depths around 11 miles beneath the surface. It climbed fast, then stalled about 2 to 2.5 miles below the seafloor. And all this was going on along the Hellenic Arc, one of Europe's most active subduction zones, where the African plate dives beneath the Eurasian region. Earthquakes often migrate across that span toward nearby islands. History backs that up. The 1956 Amorgos earthquakes unleashed massive shaking and a tsunami across the region. So, when 28,000 tremors light up the seismic network, you pay attention. This episode changed how scientists understand volcanic swarms. Now they know magma can intrude, fracture miles of crust, reshape underground reservoirs, and still never surface. It can load the system for the future without pulling the trigger today. And that matters because when magma moves like this, it changes stress fields underground and how future quakes might breed. The good news is that scientists now have really cool monitoring tools that feed real-time seismic feeds, underwater pressure sensors, and repeated gas measurements near volcanic vents into integrated hazard models. If magma starts accelerating upward again, researchers will see it and will take action. And there's another bold new idea in earthquake and tsunami warning: using undersea internet cables for this purpose. Nearly 1 million miles of those fiber optic lines on the seabed were designed to carry data, but scientists discovered that they can also detect tiny changes in light signals caused by seismic vibrations. In simple terms, when the ground shakes, the cable feels it. And this could be incredibly useful because forecasting earthquakes, even on land, is tricky. In the ocean, it has felt almost impossible as you can't scatter thousands of sensors across the seafloor easily. But those cables already sit there, stretching across deep trenches and continental shelves. If researchers use them as sensors, they can monitor tectonic movement in real time across huge areas. For a region like the Mediterranean, with hidden faults, active volcanoes, and crowded coasts, that system could offer precious seconds or minutes of warning. Seconds sound small, but early alerts let trains stop, gas lines shut down, and people move away from immediate danger. The fiber optic cable used for Seafloor Project, or FOCUS in the short version, didn't warn anyone about real disasters yet, but it had 2 false alarms. It reacted to a submarine landslide and weight bags that pushed the cables down. It proves the system works and could be life-saving in case of real danger, especially in vulnerable regions such as the Mediterranean. It shaped civilizations for thousands of years, and now science reveals it still shapes itself. They can't stop tectonic plates or cool magma chambers, but they can understand patterns, reduce vulnerability, and design cities smarter. A drought that lasted for centuries may have changed the fate of the island of Rapa Nui more than any dramatic story you've ever heard about the Moai. That slow, grinding lack of water may have quietly reshaped where people lived, how they organized their society, and why those giant stone faces stand exactly where they do. The standard Rapa Nui story goes like this. People arrived on a remote island in the Pacific. They cut down trees to move massive statues and had confrontations with each other. They ran out of resources, and their society collapsed. Researchers kept digging, testing soil, studying rocks, and analyzing climate records. The more evidence they gathered, the less the collapse story made sense. The island didn't just fall apart on its own. Something else kept pushing it, year after year, generation after generation. Now scientists think that something else was a mega drought that lasted centuries. When rainfall drops below normal for so long, the land changes, plants struggle, and farming becomes risky. Fresh water becomes the most important resource on the island. On Rapa Nui, fresh water has always been limited. The island covers only about 63 square miles, and it has no major rivers or long flowing streams. It has a few volcanic crater lakes, but they cannot support everyone during extreme dry periods, when rain disappears for decades at a time. Every drop matters. Most of the island's usable water lies underground. Volcanic rock forms the island's base, and rainwater seeps down through openings and collects below. In certain coastal areas, the groundwater slowly leaks back out near the ocean. When it mixes slightly with salt water, it can still remain drinkable if the salt level stays low enough. That narrow band along the shoreline becomes a lifeline. During a long drought, those spots turn into the difference between survival and disaster. And here's where it gets interesting. Many moai stand exactly near those coastal groundwater seeps. They cluster in places where fresh water would have been available, especially during dry seasons. That pattern forced scientists to ask a simple question. What if the statues marked water? What if they stood where people gathered because water flowed there? Some older theories said it was all about competition between clans. You know, bigger statues means more might, and more statues means more prestige. But then, researchers mapped statue locations and noticed they all had to do with access to water. And this connection looked too strong to ignore. The moai may have served as social markers. They signaled that a group controlled and protected a vital freshwater source. And in a place with almost no rivers, that control meant everything. As the drought stretched on, life likely shifted closer to the coast. Inland areas weren't that important anymore when crops struggled and surface water disappeared. Coastal zones with groundwater became centers of activity. People farmed carefully using rock gardens that trapped moisture in the soil. They used broken stones to reduce evaporation and protect crops from wind. That technique shows planning, not chaos. It shows that they adjusted to the new conditions. The statues themselves show that people had to work together and stay organized to make them happen. Some weigh up to 80 tons. Some stand more than 30 feet tall. Moving them across uneven terrain without metal tools seems impossible, but new research solved that mystery. They built a replica of a moai that weighed about 4.35 tons. For the experiment, 18 people grabbed ropes attached to the statue and started rocking it side to side. Step by step, they guided it forward for about 300 feet, and they did it in just 40 minutes. That's surprisingly quick and way more efficient than trying to move around a massive stone slab flat across logs or wooden rollers. The island itself actually made the job easier. Ancient roads on Rapa Nui were about 14 feet wide, and they had a slight inward curve along the edges. That subtle curve works like a natural guide rail. It helps keep a tall, heavy statue balanced as it walks forward in that rocking motion. Each move didn't just transport a moai, it reshaped the path too. The workers likely cleared stones and leveled the ground as they went to prepare short sections at a time. They probably cleared a stretch, rocked the statue forward in a steady rhythm, stopped, adjusted the ropes, cleaned up the next patch, and repeated the process. If you look at aerial images of the island today, you can still see traces of these ancient roads. They crisscross the landscape, sometimes running parallel like backup routes. If people did not cut down every tree to move statues, then the collapse story would weaken even more. Forests can disappear over time, but it now looks like drought played a bigger role in the story. Trees struggle when rainfall drops year after year. Weather can thin forests without humans being reckless. Genetic studies add another layer. Researchers used to believe the local population collapsed before the Europeans arrived in the 1700s. But then they analyzed the genomes of 15 historical Rapa Nui individuals and found no sign of a massive population crash in the 1600s. In genetics, a real collapse leaves a clear fingerprint called a bottleneck, which means the population shrinks so much that genetic diversity drops sharply. The team didn't see that at all. Instead, they saw that the population stayed relatively small and stable and likely never exceeded 3,000 people. That number lines up much more closely with what early European visitors recorded, and it's nowhere near older estimates that claimed 15,000 people once lived there. But there was clearly a sharp decline in the 1860s after European contact, not before. And here's another twist. The DNA also shows Native American ancestry in both past and present Rapa Nui individuals. The mixing likely happened centuries before Europeans reached the island in 1722. That means Polynesians and indigenous people from South America somehow met across thousands of miles of open ocean. Maybe Rapa Nui sailors traveled east, or Native Americans sailed west. Either way, the contact happened long before colonial ships appeared on the horizon. Archaeology adds another layer to this. Researchers found obsidian blades at the earliest known settlement on Rapa Nui. When they examined the tools under microscopes, they found tiny starch grains stuck to the edges. That's ancient food residue. Out of 46 grains, they could clearly identify 21, and those grains came from 8 different plants. Some of them made sense. Taro and yam are classic Polynesian crops. Breadfruit and Tahitian apple are also Polynesian, likely carried across the ocean in canoes by the first settlers. Ginger showed up too, probably used as medicine or spice, but the blades also carried traces of sweet potato, cassava, and achira, crops native to South America, and they found them in the earliest levels of the site. That means the first settlers didn't just survive on what they brought from Polynesia. They were already connected to South America about 1,000 years ago. Sweet potato especially stands out because it had to cross the Pacific somehow long before Europeans arrived in 1722. So when people talk about Rapa Nui as isolated and cut off, that picture doesn't really hold up. They were skilled ocean navigators. Researchers now want to go further. They plan to use isotopic analysis to figure out ancient rainfall patterns. Isotopes are tiny variations in chemical elements. By studying them in soil and rock, scientists can estimate how wet or dry the climate was centuries ago. They also want to map underground aquifers, those natural reservoirs of groundwater stored in rock layers. That mapping could confirm exactly how closely statue placement matches freshwater sources. And this way, with every new study, that dramatic "they ruined themselves" story falls apart a little more. Life on the island wasn't easy with long droughts that put everyone under pressure, but the evidence doesn't show a society spiraling into chaos. It shows people adapting. They focused on protecting the resources that truly mattered, and somehow they kept things going for generations in a place that never offered much room for error. And that completely changes how we see Rapa Nui.
Nearly 12,900 years ago. Hey, I wasn't around then. But something happened that pushed the northern hemisphere back toward the Ice Age. For years, scientists thought the cause was a huge asteroid. But new research points to something that was here on Earth all along. A volcano hidden beneath ice or underwater that, instead of melting the ice, did the opposite and made Greenland even colder. Scientists call this abrupt deep freeze the Younger Dryas. Despite how it feels with those unbearable summer heat waves around the world, Earth is still technically in an ice age. Earth's orbit and axis go through all kinds of tilting and wobbling, which is why we swing between colder glacial and warmer interglacial periods. Right now, we're in an interglacial period, named the Holocene. But before civilizations could really grow crops and enjoy summer, they had to endure this unexpected freeze that lasted for about 1,300 years. Evidence from Greenland suggests this change happened within just a few decades. Temperatures dropped by more than 27 degrees Fahrenheit, winds got stronger, and the entire North Atlantic started acting like someone turned the freezer up a few notches. In Europe's sediments, the plant record flipped back to cold climate tundra. That shift even brought back a tough little Arctic flower, Dryas, in the middle of Europe, and that's what this sudden, teeth-chattering cold spell was named after. But why the unexpected brrr? The clue comes from deep inside the Greenland ice sheet. All that endless ice is like the Earth's hard drive, with all the events sorted in order. When it snows in Greenland, the snow doesn't really melt away. Instead, more snow just keeps piling up on top of it each year. Over time, all that weight squashes the layers beneath, turning them into ice. This process captures tiny air bubbles that hold bits of the atmosphere. Basically, the frost keeps a snapshot of whatever was happening in the sky at that time. For example, if there was a big forest fire in Canada 5,000 years ago, the smoke and soot would drift over to Greenland and settle on the snow. If a big asteroid impact really happened around then, you'd expect its chemical traces to show up in the ice layers from that time. Now, to access this data, scientists use massive hollow drills. They drill deep into the ice and pull up long cylinders called ice cores. And because Greenland's ice is nearly 2 miles thick, those cores can preserve a ridiculously long climate record, allowing scientists to examine ice that's over 100,000 years old. By examining ice cores from that period, researchers found a sudden spike in platinum. This element is super rare near Earth's surface, but it's much more common in meteorites and asteroids. That's why theories were pointing to something huge from space. But how could an asteroid cause climate change? Well, basically, it works like this. Let's say a giant rock slams into an ice sheet. The impact blasts dust, ash, and all kinds of particles high into the sky, way above the clouds. Big booms can cause massive fires, adding even more smoke. Now the planet is wrapped in a dusty, smoky layer that blocks part of the sun's energy. The thing with ice is, when it doesn't melt, it spreads and reflects sunlight back into space, which makes things colder again. That loop is called the ice albedo feedback. Sounds like a cool theory for the younger Dryas. And just to make it even more tempting, Greenland also seems like it might be hiding the actual crater. Radar surveys beneath the Hiawatha Glacier revealed a round structure about 19 miles wide. Scientists were wondering if this was the one that caused the younger Dryas, but dating showed it was about 58 million years too old to be the culprit. Also, a platinum spike doesn't automatically mean a meteor. Platinum from space usually comes with a supporting buddy metal called iridium. If you find one, you should find the other. But when scientists analyzed the Greenland ice, iridium was missing. So the chemistry didn't really point to a meteor. It looked more like volcanic magma from the North Atlantic. Then there's the shape of the platinum signal. It drains on for multiple years, not one sharp boom layer. That's more like something steadily feeding the atmosphere, not one big explosive impact. So, if platinum isn't pointing to a fresh impact, the next question is simple. What on Earth can put platinum into the sky and also cool the planet? The answer is a volcano. The kind they're talking about could have been in the North Atlantic region, possibly in Iceland, and it may not have even been fully on land. It could have erupted under thick ice, or underwater. Here's the difference. When a volcano blows its top in the open air, we get ash clouds and oozing lava rivers. But under the ice, magma hits meltwater, flashes it into steam, and can explode into fine ash and gas. Underwater, powerful eruptions can also fragment magma and push material upward. In both cases, the real trouble isn't the molten rock, it's the gas. Hey, I can relate. Now, big eruptions like these spit out massive amounts of sulfur dioxide. If that gas gets high enough, like miles above the clouds, it spreads out and mixes with water vapor to create sulfate aerosols. These are basically microscopic droplets of sulfuric acid. Individually, they're invisible, but get billions of them floating together and they act like a planetary shade. From space, Earth actually looks shinier because those droplets are reflecting sunlight. But down here on the ground, it's like looking at the sun through a thin, silvery veil. You don't need total darkness to freeze the world, you just need to dim the sun a little. Summers stop being truly warm, and snow survives into July. That leftover snow compacts into ice, which reflects even more sunlight. It's the same kind of feedback loop as the one triggered by an asteroid, except in that case, the sun is blocked by dust, while here, it's reflected back into space. Something similar happened quite recently. In 1991, Mount Pinatubo in the Philippines unloaded about 20 million tons of sulfur dioxide into the stratosphere. It wrapped Earth in a thin veil, and global temperatures dipped by about 1 degree Fahrenheit for about 2 years. Just imagine the scale of the eruption if Greenland's temperatures had dropped by more than 27 degrees Fahrenheit and stayed that cold for 1,200 years. But here's an interesting question. Could it be neither? Not a climate-changing asteroid, nor a hidden volcano. There's a third suspect that's much quieter but just as dangerous: fresh water. One leading theory is that the world warmed up and a massive glacial lake in North America, often linked to Lake Agassiz, suddenly drained or rerouted, dumping an absurd amount, like quadrillions of gallons, of fresh water into the North Atlantic system. That fresh water diluted the surface ocean in regions where dense, salty water normally sinks and helps drive large-scale Atlantic circulation. When that sinking weakens, the overall circulation slows down and less ocean heat reaches the North Atlantic. With that system disrupted, the Northern Hemisphere could cool extremely fast on a climate timescale, within years to decades rather than centuries. In that version, the platinum spike could be a coincidence, a volcanic burp during the freeze, not the trigger. And in the end, if the volcano was the cause of the endless winter, could this happen again in our time? Absolutely. The North Atlantic region is still geologically active. Iceland erupts regularly, and the volcanic systems along the Mid-Atlantic Ridge are very much alive. But it wouldn't be a jump scare out of nowhere. Even volcanoes buried under the ice usually give warnings, like earthquakes. If heat builds down there, it can melt large volumes of ice from below before anyone sees ash in the sky. On the other hand, it wouldn't need to be a planet-destroying eruption. A moderate blast that injects sulfur high into the stratosphere could dim sunlight for a couple of years, just like Pinatubo did. That does not mean a new ice age will start the day after. Today's climate background is very different from 12,800 years ago. But the mechanism is real. The atmosphere can still be nudged, and sometimes